Okay, sorry folks listening at home. I forgot to start the recorder at the beginning of class because we weren't sure the class was going to make. I've talked about the syllabus, and sorry, you'll just have to read the syllabus to see what's there. This is last fall's syllabus. It's not been updated, but just the things like the dates and times, those are the only things that have changed. The rest of it is pretty much good, okay? And we're talking now about Blackboard. And what I was saying, that's what reminded me, the PowerPoint shows will be in two places. I will put them under content, that's where the syllabus and everything else is, under content. Those will be static. You can just look and see what these are. Some people like to print those off and then take their notes on them. You know, I don't care what you do with them, they're there. The second place they show up is I teach from the PowerPoint slides, so therefore everything I record on Screencast-O-Matic that gets loaded to YouTube, you'll see the PowerPoints again then, but there you'll hear me talk about them, and if I write anything, you'll see what I write about them. So you'll see two forms, static and dynamic. So PowerPoint shows will be there twice. All the shows will be there in static form before we get going too far. The ones as we go, those will be there. Now let me also tell you this about YouTube videos. I've taught this class several times using this package and saving them to YouTube. So rather than wipe that out every time, what I do, I leave all of those on there. And then when I do a new one, like today, this one will go out there, I'll entitle today's syllabus, even though we'll do more than syllabus. But this will be out there, and what I'll do, I'll take off the syllabus from last fall. So every time you go to YouTube, all those files you see at the top will be from last fall, and then go to the bottom and you'll pick up these because they always load from the bottom. So always go to the bottom and see that. If you want to look ahead or think ahead, then you can go to the earlier ones. Same stuff, but it may not be starting and stopping at the same time, but all the stuff will be on there. So the PowerPoint shows are there. Activities. Now sometimes the school posts activities on Blackboard, so look for those. We will have at least, hopefully, 2 activities that we will do. One of these is after chapter 15. We'll do 13, 14, and 15. After chapter 15, that's the astronomy 3 chapters. I'm going to try to schedule us a field trip to go to the planetarium at Stanford University. Really neat. Have any of you been there? Have you been to the planetarium at Birmingham Southern? Any planetarium? I think you'll like it. And the guy there is just so great. He really gives a good show. Okay? So we'll try to schedule a class there. Okay? And we'll do it whatever day and time fits his schedule because he has other shows going on all the time. That's, like I said, after 3 chapters, fairly early in the term. Yeah, this is a mini term, so just a few weeks away. Okay, toward the end of the term, when we do the weather and climate chapter for the meteorology, that's next to the last chapter we do. The lab for that chapter will be a trip, if we can schedule it, a trip to the Channel 13 Weather Center with Jerry Tracy. He and Kathy go to our church, so I know him fairly well, and he's hosted us umpteen times there, so it's always fun to do that. So if that can work out. Now, if we happen to have severe weather right about that time, and this is spring, it could happen, we may have to be canceled or if we get behind or something like that. So otherwise, we'll try to do that. So those are 2 activities we will do. The other labs we'll all do in class, okay? Well, there's one lab you'll do at home, part of it at home, part of it you'll do in class. We'll talk about that, okay? Assignments. Now, like I said, I'll put out your research paper assignment. It's not there yet. It's not quite ready. I'll show it to you in a few minutes. But as soon as I make a few corrections, it'll be ready to go out there. But the other assignments I will make on the YouTube video. I'll record on that, and if you miss a class, you'll have to listen to YouTube to see if there are any assignments there. Okay? So, announcements. And again, I don't usually make too many announcements. The school sometimes makes announcements, puts announcements on Blackboard. But the ones I'm most likely to make are the ones about the 2 field trips, especially if something gets changed about them. Or if something comes up, anything that spur of the moment that I don't have time to tell you about in class. On those 2 field trips, most of the time we'll talk about those well in advance. So I may not even put that. And only if a change comes up, then I'll do that. Okay, grades. All right, early in the term, I should be able to get most of your grading because it's a small class, grading done relatively quickly and out there hopefully the next day. Because this is Tuesday, Thursday, my Wednesday and Fridays, I have a lot of office hours, okay? So hopefully I'll get those out there in the next day. But, and I don't think this will happen in the first mini-term, but it might. If something comes up, like registering for the next term or something like that, sometimes I get really bogged down with that. And also making out schedules for the next term or something like that, then it may put me off, but then it might be the end of the week before I get your grades out. But usually I use Friday to catch up on things like that or the weekend. So if I don't have it the next day, hopefully by the end of the week. If I happen to have a treatment then, which I don't think I will, for this class, the Friday could be spotty too, okay? Because I can't always get internet access at the Kirkland Club. Okay. Now, this next sentence I think is way overstated. Failure to use Blackboard could severely damage your ability to pass the course. Wow, what a harsh statement. If they let me change it, I would have said the proper use of Blackboard could greatly enhance your ability to do well in the course. It's a much more positive statement to me, closer to reality. Now, some classes, it may be if you don't use it, you fail. That may be true. Not in this class. Okay. The next one makes no sense at all. See the schedule book. We haven't had a schedule book in years, but they don't let us change this. Okay. Inside cover, there is no inside cover because there's no schedule book to determine when you can attend training if you need it. So if you don't know how to use Blackboard, see me. I'm not an expert at it, but I can give you the basics. But I can find an expert if you need an expert. Okay, there's plenty of them around. And then I really don't like this one either. Students should always check the Blackboard announcement page prior to coming to class. Why would they have that in there? Comma, in case the instructor has canceled class. Now, none of you have been in my classes before, right? If I can help it, I never cancel a class. If I can't help it, I'm usually going to tell you well in advance, or if it's an emergency, I'm not going to have time to put it on Blackboard anyway, okay? So the odds are I will call somebody and have them place it on the board. But most of the time, I'm not going to cancel a class, so that's sort of okay, core student learning outcomes. This doesn't mean you're slow students, so you call it slow student learning outcomes. Okay. Students will be able to demonstrate the knowledge of stars, galaxies, and the solar system. That's basically chapters 14, 15, and 16. Now, not quite in that order, but let's see if I can scroll down so you can see both of these at once. Okay, close, okay. That's 14, 15, and 16. Actually, chapter 14 is the stars and the galaxies, chapter 15 is the solar system, and chapter 16 is the Earth-Moon system. Okay, so that's the 3 chapters on astronomy. Now, each of those chapters will have a lab. Then after the third one, we'll have another lab going to the planetarium if we can schedule it. So there will actually be 4 labs for those 3 chapters. Okay, secondly, demonstrate knowledge of rocks and minerals, plate tectonics, building and shaping Earth's surfaces. Okay? Rocks and minerals is chapter 17, plate tectonics is chapter 18, building the Earth's surface is chapter 19, shaping the Earth's surface is chapter 20. Okay? That's the unit on geology. Okay? Demonstrate knowledge of the Earth's, identify key indicators of weather and climate. That's chapter 23. So we skipped 21 and 22. That's geologic time and atmosphere. I wish we had time for them, but we just don't. These are a lot of chapters to do in an 8-week mini-term, right? Especially with me talking all day today. And then weather and climate is chapter 23, and demonstrate knowledge of Earth's waters, that's chapter 24. So that's meteorology, oceanography. And you'll work together in groups to solve laboratory assignments. Now, the first 3 assignments, the astronomy assignments will be, they're fairly thick things, and we'll go through those as a class. And we'll use some tools and other things, and we'll go through that. That third one, though, we'll do most of it as a unit, but part of that you will be observing the moon for a 2-week period. Okay, and we'll talk about that one then. So that one will have a homework assignment with it as well. Okay? Then when we get into the geology part, the first one there is going to be a computer lab. We'll go down, we'll find the computer lab, we'll go to it, and you'll do that on computers. Now, if enough of you have laptops, we might be able to do it in here. That would be fine too. Okay, the plate tectonics lab, we can't really split the price, so there are some other, labs that we will do either as group or individually, but you'll always be working with each other. Okay, either the whole group or pairs. One of those we'll actually go down and do what they call a wet lab. We will actually determine the density of some rocks. Okay, so that will be sort of fun too. Okay, do some on latitude, longitude, just a variety of things like that. And then, like I said, the one on weather and climate, that's the trip to the Channel 13 Weather Center. And then the Earth Waters Lab is just going to be a paper lab. It's just something that I'll give you the assignment, you go through the chapter, fill in the blanks. Okay? That's probably one of the easier ones. It may be a little bit more boring because you don't really get to interact, but you can work on it together. Okay? So that's working together to solve laboratory assignments, and then each one of you will do research on some topic in physical science. It's not huge, okay? Just, we'll talk about it later. Just get you out of the book into the real world, okay? And then there's a comprehensive final exam, which, by the way, will be probably one of the easiest tests you'll ever take, okay? It's not a huge, obnoxious thing. It just covers some of the, like 3 or 4 of the top topics in all of the 9 chapters that we do. So it's fairly straightforward, okay? The other test will usually be 2-page, multiple choice mostly. Every now and then I'll fill in the blank or two. I can't think of many that have calculations, but possibly. Okay? The final exam, though, is going, one actually will be a take-home test because I found the test bank to be terrible in that chapter, so I made up one. Well, I used their questions, but rearranged them some, and because of spelling and stuff like this, I want you to have your book open to do that. So one of those will actually be a take-home test. I can't remember which one. It's one of those. Okay, and then, and actually one of the labs is a very short lab, and so you'll do parts of that lab by answering questions from the book. So there's a variety of things going on with all this. The comprehensive final exam, though, is matching. So that's why I said it's a pretty easy final, I think you'll find. And let me also say this while you're here to hear it. The other 3 that are not here and the other 4 that I hope will come. In every test, including the final exam, you can have in your possession a formula and equation sheet. Anything you want to write down on a piece of paper, any definitions, sample problems, you don't have many of those. Anything you want to write down on a piece of paper, you can have with you during the test. Because some of the tests can be, maybe just a little picky. The choices between the multiple choice are pretty close. So if you want to, I don't like for you to memorize. I want you to know. So I'll let you have that formula and equation sheet. And a lot of times, come the first test, people forget to do it. After that, they'll say, "Yeah, I think I need to do a formula and equation sheet." But even on the final, you can have that. Now, that take-home test, you won't need one because you'll have the book open in front of you. Okay, any questions on that? Okay, so that's how we're going to measure. How are we going to evaluate? How will I evaluate what you did on that? And they always start this with this sentence, which I find is just redundant, but they have it in there. Research paper is required in the class. Notice the verb required. It will count as a test that cannot be dropped. It's required. Okay? So, do your research paper. And again, it's not any huge thing. Just do it. Okay? We'll have a chapter test at the end of each chapter. And that was, I think, 9 chapters. 13, 14, 15, 16, no. 14, 15, 16, 17, 18, 19, 20, 23, and 22 and 23. Something like that. 23 and 24, whatever they are. Okay? After each test, you'll have a chapter test. Now, that lowest chapter test score may be dropped if it helps your grade. Okay? Now, you say, well, how could it not help? Well, if you don't turn in a paper, that's a big fat 0. You need every test grade you can to pull that up. Okay? Or if you do real poorly on the paper and do really well on the test, then again, the test will pull up that. So, if it helps you, I'll drop your lowest test score. Not the final one. No. There'll be at least one laboratory assignment for each chapter covered. Like I said, each one of the first 3 have one, then we have one at the end of that. Now, those that are field trips, I can't make you go on a field trip. So those will be optional labs, and we'll talk about this in a second too. And I'll tell you what that means. So anyway, and if you go, you get 25 points. Okay, if you don't go, you don't get it. 25 points. Okay, so only benefit to go. All right, the low. Okay, there will be at least one lab assignment for each chapter. The field trip to the planetarium is one of the field trips. That would be in a 4th lab for those 3 chapters. Okay, the lowest lab assignment grade may be dropped. So let's say those 9 chapters we have, let's call it 8 chapters we have, that we actually have a physical lab. I'll hand out paper, you do it, whatever, okay? The field trip to the planetarium and then the one for the weather, those are optional. So of those 8, you get to drop your lowest, okay? If you go on one field trip, then you get to drop your 2 lowest. If you go on both field trips, you get to drop your 3 lowest, okay? So going on the field trips can only help. Okay. Laboratory grade will be averaged from the remaining laboratory assignments. And by the way, each of the labs are worth, okay, let's go back a minute. Remember, it's a 4 credit hour course. 3 hours of those are theory, book, lecture, test. The 4th hour is lab, right? That's 1/4 of the 4 hours. So therefore, I make your lab score 1/4 of your grade. So I'll do all the labs based on 25 points. That's why I say you get 25 for going on the little thing. So that will be, so I'll just add up all your, average your labs, drop your lowest one if it helps you, and that will be 25% of the grade, okay? The average of the papers that can't be dropped, and the remaining test scores, if I drop one of those, and the comprehensive final that cannot be dropped, will count as 75% of the final grade. The comprehensive final exam cannot be dropped. That's a measure of your overall learning. But again, it's going to be one of the easiest tests, so you really want to take it, okay? Whether you think you do or not, it's really going to be pretty straightforward, okay? So what I'll do, I'll average all those together, take 75% of that, add it to the 25 or so points that you get from your labs, that's your 100 points. Make sense? Okay. And then once I do all that, if you're in the 90s, you get an A. In the 80s will be B, 70s will be C, and please don't go down to anything below that, okay? You almost have to not be here and not take tests and not turn in labs. That's about the only way. I can't say the only. I have had a few C's, but even most of the time there, they've missed some labs, okay? I can't think of any C's that have actually because they couldn't comprehend the material, okay? So maybe it could, I don't know. The labs, we do them in class, we do them together. I ask see if there's any questions. If you do them, you're going to get 75%, close to 75% of your grade, right? I mean, 25% of your grade right there. And everything else, that can pull up a lot of error, okay? And your final's easy. The paper you should get a good score on. So there's no reason to be down below. Okay. Like I said, there's almost people who don't come and don't turn in stuff. Okay, attendance, you're expected to be here for all the classes for which you're registered. If you're unable to attend class regularly, regardless of the reason, I know the students, oh, but this was an excuse absence, I have a doctor's excuse. Well, guess what? You weren't here, you didn't get the material. Whether you call it excuse or not, you missed material. If you miss too much material, you're probably not going to do too well on tests. Maybe you miss some labs, not going to do well on that. You need to be here, okay? So if you can't be, and it's going to pull you down in that D or F range, think about withdrawal, okay? Before poor attendance interferes with your ability to achieve your learning outcomes. Withdrawal of your class can't hurt you academically. Now, here at Lawson, a D is a passing grade, technically, but you can't get credit for the course with it. If you make a D, to get credit for the course, you have to retake the course. You can take another science course and do it, but you can't get credit for this one with a D. And certainly an F isn't going to do it. D's and F's don't transfer either when you go to a four-year school. They don't transfer D's and F's, so we don't do credit for them. Okay? Also, a D pulls down your grade point average, right? Because it's only one quality point. And most of you, other quality, have better than a 2.0 grade point average, so a 1 is going to pull you down. Okay? A 0, which you get for an F, is definitely going to pull you down. No way to go but down there. Okay? Whereas a W doesn't affect your grades at all. It does not affect your grades at all. So if it looks like you missed enough classes or tests or labs that you're going to get a D or an F, go and think about withdrawing. Okay? Don't mess up your grade point. Now it says it can mess with your financial aid, but guess what? The only way it messes with financial aid, if you make a D, F, or a W and have to repeat a class, usually financial aid will pay for one retake. Okay? If you make another, either D, F, or W, or some combination of them the second time, it won't pay for the third class. Okay? But guess what? It's not going to pay for a D, it's not going to pay for an F, it's not going to pay for a W. A D and an F hurt your grade, a W doesn't. So look, all three of them hurt you. You have some financial aid, so why not do a W rather than a D or an F? That won't mess with your grade. Now, if you are making a C in the course and you want an A or a B and you want to withdraw for that reason, that's up to you. Okay, financial aid, I don't think will repay for you to take a class if you make a B or a C, an A, B, or C, I say. So I don't even see a reason for that. But anyway, that's up to you. So before you withdraw, see your advisor or financial aid office. Makeup work, okay? Now, the laboratory assignments are usually due 1 week after we're doing them in class. Now, there's two reasons for that. Number one, if you have any questions over them, you can ask that in the next class period before they're due. Okay? Number two, you always have a weekend in between. Because if it's 1 week in between, there's always a weekend to work on. But guess what? Hey, most of the time, the labs are going to do in class, and they're you'll probably finish them when we finish the class. Maybe not everyone. There are a couple of exceptions to that. One of those labs, remember, is going to have some questions in it from your text. Okay? So that lab you'll take home and do part of that at home. You can work on it in here if you want to and work together to answer those questions, or you can take it home and do it. So that one usually people turn in, next class period or a week later. The Moon Lab, you're probably going to be 2 weeks on that, at least 2 weeks, because you've got to observe the moon for not every night, but about every other night for 2 weeks and fill out some information on that. So that one won't be due a week, but it's a week after it's completed. So that's 2 weeks after we do it in class. Okay, we'll try to start all the classes at 12:30. Now sometimes, like today, I couldn't even start lunch because I was talking with an instructor, then my boss came by, and then I had to make some arrangements. And then about the time I was going to start eating lunch, a student came by, and I had to deal with that. And then I crammed down lunch. The phone rang. I had to deal with that. And I just barely got lunch eaten before I got up here. And I was a couple minutes late, and I was in the wrong room. Okay, so most of the time I'll be here at 12:30. But I can never tell what's going to happen with my people stopping me in the hall or whatever. But most of the time I will be here. And then we'll go 12:30 to 5, just about every day. Now, I'll give you some, let's go and do a little bit of an explanation there. Today's unusual because it's the syllabus and research paper and locator card and safety and all those kind of things. So the day's going to be weird. It's going to be the last part of the day before we even get into physical science. But we will get there. Okay. Most days we'll have lectures the first part, and if we're ready for a lab, then we'll do the lab the last 2 hours, just like it's scheduled. But if we finish a chapter, say on a Tuesday, we'll have the test in that chapter the next Thursday. Now, if there's a lab also that Thursday, what we'll do is have class for 2 hours, lab for 2 hours, and test for the last 30 minutes. Because the tests are all multiple choice, a few short answers, and the final is matching. So they're all pretty quick tests. If you need to take more than a half hour, I'll be here. You know, I have nothing that says I have to leave right at 5 or 5:15. I'll be here as long as it takes. So I always schedule the test to be the last 30 minutes. That way, when you finish the test, you can go home. I always schedule the labs to be either the last 2 hours or the 2 hours before the test. So if you finish the lab early, you can start the test early and you can go home, okay? But I don't want to give the test at the beginning and then, 3 of you finish early and the other 4 are taking longer, and then finally we get started, and so you have to sit around and wait. So when you finish the test, you can go home. The other thing with the labs, if that's all we're going to do, class and then lab, I don't have to wait till everybody finishes the lab, and everybody else sitting around. We do the lab at the end, and when you finish, you can go home. Okay? So that's why I schedule it that way. So we may be having lecture on one chapter, but lab on the previous chapter, and the test on the previous chapter. That could happen, okay? But they all tie together, so I think you'll find that's not anything that's difficult. Okay? All right. Now, if you do miss a class on the day we have a lab, and we're going to have lab just about every day, okay? Then you'll have to come and get the lab from me. Now, I'm going to record as much of the lab as I can on Screencast-O-Matic, and it'll be out there on YouTube. So get as much as you can from there. If you can't get enough, because like if you're taking measurements or something like that, or when you do the computer lab, we're not going to call out the answers to all those things. Everybody's going to be doing that on computers. You'll have to be doing that at home. If you have questions, come see me. We'll, during office hours, and we'll work through that out. Okay? So try to have the labs turned in within a week of when they're given. Now, of course, if some of you are, say, National Guard or reserves, military, or something like that, and you have time you have to be away, we make accommodations for that. You get the flu. Yeah, we understand. We don't want you here if you got the flu. We don't want you exposing us. So we make accommodations. Okay, let's look at the statement on discrimination and harassment. See this on just about every syllabus. So I'm not going to go into great detail on it. Let me say this first. Discrimination, don't want it to happen. Harassment, don't want it to happen. I always include in here, I think it's included in that, things like bullying, that kind of stuff, don't want it to happen, okay? And I'm in, I think, my 21st year teaching almost in this room, okay? Taught in other classes when I've had other rooms when I've had too big a class to fit in here. But most of the time I've been up here, that's why I moved to some 259. That's a big room, and for 7 students, we didn't need that big room. We may go down there and do one of the labs down there, but we'll take care of that when it comes time. But in the 21 years or so I've been here, I have seen basically almost nothing that fits in those categories. Now, I'm not saying it hasn't happened, I just haven't seen it. But I haven't heard of it happen. So therefore, I want you to be my eyes and my ears, because guess what? If someone's going to bully or harass or discriminate against someone, the odds are they're not going to pick to do it in front of an instructor, especially a mean, ugly, big, ugly, hairy person like me. They probably won't do it. They'll do it behind my back, and I won't do it. They hear about it later. I want you to be my eyes and my ears and my senses there. Let us know. If you sense or even think someone's being bullied or harassed or discriminated against, let us know. There are procedures in place. Even if it's us, we'll help you write our stuff up, okay? Or my boss will, or someone will do. We don't believe it. Let me point something out to you. Any practice or behavior that constitutes harassment or violation of State Board of Education policy and will not be tolerated, okay? Then look at this next one. Harassment of any nature is never tolerated. You get the idea? We don't want it to happen here. We take those charges seriously. Now, we're fair about it. We're quick about it, okay? I'll give you the example that comes closest. It really doesn't fall under here, but it's a decent example. It's only like the second or third year I was teaching here. I used to teach automotive math we have a great automotive program over there. They're on co-op system. That's why these are mini terms. Because the second class, the Physical Science 112, Physics and Chemistry, the automotive students need that to graduate, okay? And because they do, we have to offer a second mini term because those that are in the Ford, Toyota, and the GM programs, they in school for the 8 weeks and it works for 8 weeks. That's the first year. Second year, they're at work for 8 weeks and then in class for 8 weeks. So they just flop out half their classes there. It's a 2-year program. And it's the second year students who need the Physical Science 112. They need it on the mini term, second mini term. So I schedule first mini term to be 111 because I have this half a term empty that I can teach 111. Okay. Where was I going with that? Oh, way back, I had the automotive students. A lot of them are right out of high school. Now, some of you may be, but a lot of them are not a lot. Occasionally, we'll get some of them that are very young and immature. And we had this one kid, I swear his dad must have made him come to school. He said, well, I want to do auto mechanics. He really wasn't interested in that. He just thought it'd be fun to do. But he was not a serious student. He was doing really poorly in those classes and these classes. And one day, we met after lunch. And one day after lunch, he was absent. Most of the time he was here. And this is fairly early in the term. So I called his name. I looked around and said, he's not here today. He said, oh, he won't be back. I said, why? And then they told me. One day at lunch, the previous day or so, he had just decided to go out to the parking lot and walk across people's cars. You know, they were parked right next to each other, jump from one car to another car. He thought that would be a fun thing to do. Well, someone saw him, yanked him off, took him to the dean's office. I don't know how long he was there. I don't know what the volume was, but it wasn't there very long before he was packing his bags and leaving campus and never seen again. Okay? Now, that was a little abrupt, but that's basically what we feel about harassment, discrimination, bullying. We're going to give you a fair shake, but it's going to be quick, it's going to be thorough, and hopefully it will be, like I said, fair. Okay. This next one we also see on every syllabus, so I won't go into huge detail on it. Okay. It's Americans with Disabilities. These are federal laws, there's probably state laws going with it. Basically, if you have, and by the way, if you haven't noticed, I'm hard of hearing, okay? And I ask you to repeat your name or something like that. It's not because being obnoxious, I probably am obnoxious, but that's not why. It's just because I don't hear well, okay? And that's probably, I talk too loud. I can't tell, but most people say I do, okay? So, it's my lack of hearing. So I'm sort of sensitive to disability. I mean, mine's not major, but some people do have fairly major disability. We want to make it so you can learn. That's what we're here for. So if you have a disability, whatever it is, vision, hearing, some of those letters, ADA, whatever, you know, and dyslexia, any of those kind of things, please let somebody know about it. You can tell me, I'll send you to the professionals on it, but it's your responsibility to provide the documentation to the college. I can't assume that you have a disability because as soon as I do, I may be discriminating against you. It may be that your eyes just squint all the time, you know. So I can't assume that you, because I see you squinting, you have an eye problem. On this campus, we have Dr. Renee Herndon. She's in charge of the Office of Disability Services. In fact, she's in charge of all our counseling services. There's her phone number. She's on the Vassar campus most of the time. Mrs. Janine McCoy Jones She's on the Birmingham campus. There's her office number on the Birmingham campus. Or you can go to the Austin State website, and there is a place there you can request a meeting online. That can be arranged. Okay? And there's how you do that. Here are the locations, the physical locations. Okay. On the Vesper campus, it's in this building, down on the first floor. Did most of you come in the student services entrance? And you saw that admissions desk there, sort of a curved desk, fairly nice looking desk. Okay. You came to the right side of that, came down the hallway to come over here. If you go on the left side of that desk, and there's a very short hallway, go almost at the end of that hallway, take a left, and there is Dr. Herndon's office. Actually, you can go to the information of the admissions desk and just ask for Dr. Herndon or ask for an ADA counselor. They will give her a ring. She'll come right out there and meet you. So she's just a few steps away. Okay, on the Birmingham campus, it's in the Leon Kennedy Center building. That's on the first floor is the cafeteria, the police, and some other things like that. On the second floor, there's the bookstore, but also the Space Center. And that's where Miss McCoy Jones is, at the Space Center, and that's where the chief engineer is. Now, this course calendar is actually the college academic calendar, and it's not correct, okay? This was last fall. So I will get this corrected, but you know, classes started today. We have drop-in ending next Tuesday. Martin Luther King Day is next Monday. Last day to withdraw, I'll have that day. I'll have all those dates on here to match. Of course, we don't have Thanksgiving, but we do have spring break. So I'll have those dates on here. There will be a date listed for honors and awards, but that's going to be in the morning on a Thursday, so it won't affect this class unless it gets out late, and then maybe we will start a little later. But no, actually it's in second midterm, so I don't think we have to worry about that. So I'll have all that information out here. When your final exams are, and actually that's only one day, so it's not going to be a week like this. That's for the whole term courses. Our final exam is that last day, last Thursday. Okay, and then when the final reports are due, I'll have all that information there. Okay, and then the last thing is once you've read this corrected syllabus, I get it on Blackboard, I'll let you know when it's there, then you can either print out this and write your name and date, or you can type this in and email it to me, whatever, just that you understand, you've received the syllabus, you understand it, you had all your questions answered. Any questions right now? Pretty exciting stuff, isn't it? Okay. All right. If there are no questions, then I'll go on and close this down. And I'll get this corrected and out there. I probably won't do it until after I find out if we're going to have the class on. We're going to meet next Thursday. We'll find out then if we're going to cancel the class or not. Okay. So let me get research paper. Okay. Now, here's the general instructions for it. I've got a couple of changes to make, but most of it the same. You get to choose a topic. And boy, this class has lots of possible topics. You can do anything to do with astronomy, planets, stars, systems, galaxies, solar system, whatever. Comets, neutron stars, I don't care. I mean, black holes, I mean, anything like that. It could be a theory. Okay, we'll actually talk about, not the television show, but Big Bang Theory, okay? You'll talk about other plate tectonics theory, so any theory that you might want to choose. A person, okay? And every chapter will have at least one person they mention, do a blurb on in the back of the book or end of that chapter. Guess what? That's not your resource for your paper. You don't just think you can type that. I know what those say. I'll recognize it if you do. Don't do that. You can get ideas from the book, but you need to go and get your things elsewhere. So it can be a person, a phenomenon, nova, a supernova, a collision of two black holes. I mean, there's all sorts of, and look, I've only hit the astronomy part. Rocks and minerals, plate tectonics, meteorology. There's people in this. There's theories in this. There's phenomena in this, okay? Thunderstorms, tornadoes, earthquakes, tidal waves, tsunamis, any of those things would be legitimate topics. You pick your topic that you have an interest in. Or you could do it on an internet application or demonstration. Now, I can't think of that many that would be appropriate for this class, but if you find them, that would be fine, okay? If you find something out there, say on Khan Academy, I doubt if they do anything like this, but on some website like that, that you think, wow, this really explains this far better than the book did and that guy did, you know, so you can certainly use that as well, okay? Now, what I'd like you to do, either today or Thursday, or you can wait and see if the class is on me, write your name on a piece of paper. That's pretty simple, isn't it? Then also write the topic you think you may like to pursue. I want to get you thinking about it now, because guess what? We only have 8 weeks. That means 8 weekends, okay? Yeah, not that much time. So get started on it now, okay? So write the topic on that piece of paper and give it to me either this week or next week, okay? Now, since that's going to take up so little space on that whole piece of paper, here's something else you can write there if you want to. It has nothing to do with research paper, but it has to do with being able to get in touch with you. I spent most of Thursday and Friday and yesterday trying to call students whose classes have been canceled, see if I could help them do that. And not as frequently as it used to be, but way too frequently, I hit a number that was disconnected, no longer in service, or if somebody say, hey, we've had this number for 10 years, that person never heard of them, okay? They were just in the system wrong. So periodically, because that does happen, we'll get some, say, minor emergency or something happening, and someone will call me and say, look, I need to talk to thus-and-so because she's in your physical science class. Can you, do you have a better number? The one in the system's not working. And therefore, if you want to give me your very best phone number, you can. It's not required, only if you choose to do so. Now, my guess is most of you will give me a cell number, right? But if there's a chance that cell phone could be lost, the battery die, get run over by a car, you leave it at home or something like this, if there's a good backup number for you, on this landline or something like that, if you want to give me that one, you can. That's completely up to you. And a lot of our students work. I don't know if y'all do, but if you happen to work and the times of day when they may be trying to reach you might be when you're at work and you can't use your cell phone at work, but you will be able to take an incoming call. If you want to give me a work number, you can do that too. You don't have to give me any of those. You can give me only one, only two, only three. I don't care. But if you want to give me your best number, I'm not going to give it to anybody except someone here at the college, not a student, someone here at the college in the administration that is in desperate need of finding you for some type of emergency or something. I probably won't even use it unless something comes up that I really need to get in touch with. Okay? So, write that. Now, when you're in the process of doing your paper, you'll need to find at least one, but 2 or more are better, outside sources for your paper. Even though there's great blurbs in the book, there's great descriptions in the book, there's a huge description on, what is that called? El Nino, okay? That's a great thing to write on, but you can't use the thing out of the book. Even though it's a great resource, you can't use it. It needs to be an outside source. The book can give you the ideas, you have to go outside to get it, okay? Those can be books, journals, articles, newspaper, magazines, anything that you can find in the library, okay? Or online, in the library, or any legitimate source found on the internet. Now, there's a big problem, isn't it? There are a lot of people don't allow internet sources. I do, as long as you know it's valid. Now, I tell my classes this. If someone pressed me with the question of what's the greatest thing that's ever been developed in your lifetime, I think I'd have to say the internet, because I was born, unfortunately, in 1951, a long time ago. I don't believe it existed then, so it's been completely developed in the time I've been alive, and it is incredible. It is amazing. Basically, you have all the information in any library in the world at your fingertips. I mean, it's just incredible what that is. And yet, there's 2, probably a lot more than 2, two big problems. One, at least half of the stuff on the internet is total garbage. Okay? Number two, sometimes you don't know which half. So before you take something from the internet, if you're at all suspicious that it may not be legitimate, please run it by me. Now, I may not be able to tell, but if it looks suspicious, I say try to find something else. So a lot of the stuff on there is great stuff, but a lot of it's not. The textbook is not an outside source. You can get ideas from the textbook, but don't use it as a source for your paper. Now, how long does the paper need to be? At least one word process page of text. Okay? Now, what is a word process page? Number one, it's not handwritten. I don't even care for typewritten. Okay, I want it word processed. But what do I mean by one page of text? Now, I don't care how you format your paper, but I have a lot of students that probably because of English class, they use some sort of format that has a header on the top and things up there, and then they skip a few lines, and then have the title, and they triple space, and then they start typing. One page of text is going to start right there, that typing, not up there, but starting here, go to the bottom of that page, and on the second sheet of paper, start at the top and come down and go at least that far. That's one page of text. So it's always going to be two pieces of paper at least. Okay? So one page of text, at least one page of text. But this is single space. You can double space. In fact, I want you to double space it. It's easier for me to read, easier for me to make notes on. Okay? If you make errors or I have questions about it. Okay? So double space, and I want your standard font. I think this is 12 pitch or 12 point, whatever you call that font. I don't want 26 point, that 3 words fill a page. That won't work. You know, that's not going to be your paper. Okay, so standard that. The font's up to you as long as I can read it. I don't read hieroglyphics or Old English or Greek or Cyrillic or any of that. Keep it something clean, neat. Most of the word processing defaults to Times New Roman. Fine, I don't care. I happen to use Arial here. Great, I like it. Courier. There's tons of great readable fonts. Use whichever one you want. But be consistent. I don't want one font here and another font there, and here a font, there a font. No, okay. So, now, try to keep the paper less than 2 pages. The only reason I say this is so it won't be so hard for you. But if you get so fired up about the subject and you find so much great material and you go over 2 pages, I'm not going to take off points for being too long. You will lose points if it's too short. You won't lose them for being too long. Or at least not directly. Now, I hesitate to say this, but I have had it happen. Not often, but a few times in the past. I swear somebody decided, well, I can't do quality, so I'm going to do quantity. And really impress the fire out of them, okay? It's not going to work, okay? If I get a great big long 15-page paper, I'll read it. I promise I'll read it all. But here's the deal, folks. When you turn in your paper, it's a 100-point paper, okay? Then I start reading it, okay? And if I find errors, you start losing points, okay? And don't say, don't read it, don't read it. No, I'm going to read it, okay? I'm going to read all of it, okay? You start losing points. So if you turn in to me 15 pages of garbage, poorly edited, poorly checked, and everything else, you're losing points like crazy, okay? Turn me in a good paper, whether it's 2 pages or 5 pages. If it's a good paper, you probably have already taken care of all the errors. I'm going to enjoy that paper, okay? So, no reason, don't try to replace quality with quantity. Give me a quality work. If it's longer, fine, I like it. But if it's shorter, just keep it at least 1 page of text. Don't be 2 pieces of paper, but at least 1 page of text. So shoot for 1 to 2 pages, okay, of text. All right. If it's less than a page, you'll lose point, blah, blah, blah. You can use any standard format you want. I know the English classes usually teach MLA, Modern Language Association. Fine, I don't care. A lot of scientific organizations use APA format, which is American Psychological Association. They came up with a format early on, and people said, wow, how can you beat this? This is great. So a lot of organizations use APA format. It's fairly standard. When I was in grad school, my professor required us to use CBE format, Council of Biological Editors. Okay, right, we did it. I'm a member of 2 or 3 professional organizations that publish papers. They each have their own format. You know, I don't care what format you choose, but get it and stick with it. It's like if you start blocking paragraphs like I did, block all your paragraphs. Don't block the first 2 and then did the next one and then did the next one more or less. Or, you know, be consistent. Make sure your paper looks and reads well. Okay? Looks good and reads well. Okay? And other things of format. Okay. Spelling, grammar, sentence structure, that kind of stuff. Same things that lose you points in English or lose you points here. I probably won't count off as much as they do in English, but if you do have the errors, you will lose points. Okay? But every word processing package I know has spell check and grammar check, right? Use them. Okay, there's no reason not to. Okay? But I promise you, I have papers turned in. I know they haven't used them because obvious things are misspelled, and it's not just the word is used in 2 different ways, like TWO and TOW. Not that. Things just grossly misspelled. Okay? And use good proofreading. When I was in high school, I had a really good English teacher in high school, senior year, and she used this terminology I really like a lot, and I'll say it again just by every term. She assigned a research paper, maybe more than one, but I remember she'd say, get it done early, set it aside, and she used the term, let it rest. Okay, I thought, what is she talking about? Pick it up then a few days later, maybe over the weekend or sometime, let it rest for a week. Pick it up and read it, and here's the term she used, with fresh eyes. Read it as if you hadn't seen it before. And then if you stop and say, wait, what am I talking about? What is that referring to? If you say that after a few days, the odds are I'll be saying it too. And you will. Because when you're typing the thing, you know exactly what your train of thought is. You know exactly what that's referring to. But when you read it later and you've forgotten, well, what was I thinking then? It's not making any sense. So use good proofreading. Okay? Now, content also matters. One of the examples I usually give, if you're writing on a person, quite often people, when they first introduce a person, they'll put in parentheses the year of the birth and the year of his death, and then tell about it. And then sometimes over on the second page, they'll say, and this guy died at a different year than what he was listed there. I go, whoa, that was a long illness. No. Be careful. You know, be consistent in your paper. Other than Sir Isaac Newton, I don't know, maybe he did something in 1479, okay? But I remember one paper had it in 1947. No, he didn't, okay? He wasn't alive then, you know. So be careful. Content also matters. I've had people write on Pythagorean theorem and give it to me wrong, you know. I'll know most of these things, and if I don't know, I know how to look them up. So if something looks suspicious, I'm going to check it out. Okay, when is it due? The last day of class before final examination week. Now, we have our last day of class on Tuesday of finals week, and then our final is on Thursday of finals week. So you've got to have it in that Tuesday. If it's that Thursday, you're losing points. Okay? But guess what, folks? You have more time right now than you'll ever have later in the term. Because in just a few days, we're going to be having labs and having tests. And then in other subjects, you'll have labs and tests and papers and reports and Blackboard and all this stuff. Get started now. You have more time now than you'll ever have later. Now, you will lose points if it's after the first day of class, after the last day of class. But that's the stick. Here's the carrot. If you submit it, and this is the thing I've got to change. If you submit your paper, let me start at the end. If you submit your paper, this class is January, February, and the first week of March, right? So if you submit your paper that first week in March, you don't get any bonus points. If you submit it in February, you get 1 bonus point. Submit it in the month of January, 2 bonus points. Okay? So this would be, you submit your paper in the month of January, you get 2 bonus points. In February, you get 1. March, you don't get any. You get your score. If it's after the last day of class, you start losing points. Okay. When you submit your paper, this is one thing I require that most others don't. I want you to attach a single page from one of your sources. So let's say you got a book from the library or a journal or magazine. Take it over to the copier, copy me off a single page from that. If it's something you got off the internet, print me a single page from one of your sources. You may have had 3 or 4 sources. Pick a source, any source. Pick a page, any page. Print me one page from that source. Okay? Any questions? I'll get the months corrected, and I'll get this out there on Blackboard under content. Okay. Let's close that out. Okay. Last thing we're going to do in Word is this. This is my locator card, and for first mini term, I've got 1 correction to make on it. Actually, probably 2. Well, maybe 2, possibly 2. My first class did not make, so I have office hours from 7:45 until 9:30. Okay. My first class on Monday, Wednesday, then that did make is Cal 1. It's a 4-hour course, so it's from 9:30 until 11:10. So I'm back in the office about 11:15. Now, I arbitrarily put down I'll be at lunch from 12 to 1. Some days I'll be meeting with students at 12, and it may be 12:15 to 1. Whatever, it's sometime in there. But usually I bring my lunch most of the time. I eat in my office most of the time. You can come by. I'm in the office, that's fine. Now, if I'm in the middle of lunch and you have something pretty complicated, I might say, well, can I catch you? As soon as I finish this, I'll come get you. Okay, but then whenever lunch is over, I allow myself an hour. I usually don't take a full hour. But from 1 o'clock, right now it's 1 o'clock until 2, because I think I will have to pick up that developmental math class. That goes from 2 to 3:15. So then I have a class in here 2 to 3:15. Then I have office hours again from 3:15 to 5:15. You can't see, but that's that will be when I leave campus. Okay, that's Monday and Wednesday. So just insert the 2 to 3:15 math class. Okay. Tuesday and Thursday, that's the days we meet. 8 o'clock class, 9:30 class. So 10:45 to get out of class. There's supposed to be, hey, I've got to change this. I've got some things in the wrong. I need to put office advising here. But at 11:30, I try to start lunch, so I'll be through by 12:30, which is when this class starts. And this is 12:30 to 3, and at 3 o'clock we start lab, 3 to 5, and 5:15 I'll leave. Okay? So that's Tuesday to Thursday. Friday, I'm on the Birmingham campus, academic building, B122, office hours from 7:45 until 11:45. Now, most of the time I'm out there after 11:45, except on those Fridays when I have treatments, and then I'm off campus all day long. And there may be other things that come up. Meetings. I think we do have professional meetings one weekend coming up in this term. So I'll let you know those ahead of time. Any questions? I do need to make 1 correction here. In fact, I think I'll do it right now if y'all don't mind. Oh, no, I hit the wrong thing. Paste. Okay. There we go. Okay. So, and usually I'm off campus. Leave campus about 5:15 every day Today I'm going to leave as soon after 5 as possible because I have a meeting downtown Birmingham at 5:15, which not going to get there on time, but I'll get there as soon as I can. Some other days I may have to leave right at 5:15. Most days I can be here a little past that. Okay. All right. Any questions? No. Goodness gracious, this is a pain in the neck. Okay, let me save that file. Okay, and exit. There's my. Okay. Now, before we get going on physical science, one other thing we have to hit is safety. There's 3 aspects of safety we need to talk about, you need to think about. You need to sort of already have it programmed in your head, so if something happens, you basically don't have to stop. Oh, what do I do? Okay, you already followed it through. Any ideas what these 3 things might be? Weather! Very good. What might be safety issues about weather? Especially at this time of year. Not this time, but springtime. Tornadoes or severe thunderstorms or anything else that you hear that siren go off. Okay, now they have test times, what, 11 o'clock or something, first Wednesday of the month, something like that. Don't worry about those, okay? In this class, if you hear it go off, probably going to be some sort of weather issue. What do we do if there's a weather issue? If you hear that siren go off, what do we do? We're going to get in the car and try to beat it home, right? No! No, 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 no. What you do with a weather emergency is go low and interior. You hear them talking about this all the time. What do I mean here? Here we are in this classroom right here. We go out of the door, hang a left, go down that half flight of stairs. At the bottom of the stairs, hang another left. Go down one more flight of stairs. Then you're on close to the lowest level in this building. Okay? There is another few steps below that. But when you go down there, you're in the lowest level. Think interior. Don't think exterior, interior. So you're on the lowest level, then think to the inside. Now, actually, the other thing to think of in case of weather emergencies, say especially tornado or severe thunderstorm or something, what you want to do is get in a small space, okay, where the walls are close together. And frankly, and now this is second floor, but the first floor is a lot like it. The restrooms there, believe it or not, are some of the safest places to be. Why? Because the walls are close together and you have a lot of corners. Corners are much safer than open walls. Because here you have strength on 2 sides, here you only have strength, laterally. Here you have it perpendicular. A lot of strength there. So think small space, close walls, corners. So the restrooms aren't bad. Unless you're going to be down there a long time, and then maybe not the most favorable place to be, especially if the power goes off, because there's no emergency lighting in the restroom. So that might not be the most pleasant place to be during a weather emergency. So what's next? But they are safe places. Right next to that on the first floor is a small office. Right now they have like 2 or 3 steps. There is a small office at the academic dean's office. Now, most of the time she's not over here. Occasionally, either she or the associate dean might be over here. And occasionally, there might be another guy who uses the office. So, if any of them are there and invite you in, again, that's an interior space, small space, close walls, lots of corners. Safe place to be. Okay? After that, below this, here, this is room 254. Downstairs, it's room 160. If any of you had developmental math, that's probably the room you were in. Okay? 160. Now that's a big open space. The middle of that room, not too great to be in during a weather emergency. But that back wall back there, the one this side, there's no building over there. There's soil there. That is a safe, strong wall there. The corners again are safe, safer than the open wall, and certainly the middle of the room. So that's not a bad place to be if you can get that back wall or one of the corners. Okay? Now, right next to that, right past that room, you go first door on the right is a computer room. Now that's a smaller room than this one, and that's a fairly safe area. Smaller room, lots of corners, and especially that back wall against the floor. You got a lot of support there. The next room to that is a what I call a reference room. I don't know what they call it, but that has your atlases, your globes, you know, that kind of stuff. Again, the back wall is safe, the corners are safe. It's a bigger room than the computer room, probably not quite as big as the classroom. But the other thing is it does have shelves of books. And if we really had a bad storm, the shelves could, you know, I don't think they would, but you know, that would be a watch thing. So those are there. Now actually one of the best places to be, weather emergency, is the hallway. Because here the walls are close together. You don't have any corners, but what you do have, in case we lose power, and with tornadoes you can easily lose power, you have emergency lighting at both ends. So that's probably going to be the place you're going to wind up if it's a real weather emergency that's pretty serious. The hallway is not bad. Stay against the wall if possible, and you know, if you need to be in the light of that. Do not go to the outer rooms there, because those have windows. Windows are not good to be around in case of a weather emergency. Tree limbs, other things could get thrown through the window, glass could shatter. You don't want to be there. So anywhere else in the library is not a good idea, because that's on an outside part of the building. So avoid that. So go low, go interior. Close walls, corners are best. But you may want to consider emergency lighting and things like that too, in case you lose power. All right. Now, here's another thing to think of with weather emergency. Do like I say, go to that place. Other rooms will go to other parts of the building, and other rooms will go to that part. I'm going to be the last one out of this room. Now, right now, all three of you are pretty healthy looking people, okay? There's 4 people we haven't seen, 3 paid students we haven't seen, 4 unpaid students that we hope we'll see. What if one of them or one of you is in a skiing accident or something like that, and you're on crutches or in a wheelchair? That's really very inconvenient in a building like this, because we don't have any elevators. We do have 2 stairwells that have platforms that go up and down, but they're not easy to get to. But generally, I'm going to be, if anyone is impaired, mobility impaired, I'm going to be with that person. And I might actually need one of you other fairly strong, able-bodied people to be with me, and we'll help that person down. But I'm going to be the last one down, and I'm going to carry with me the roll book. And when I get down to that lowest level, I'm going to find you and call roll. If I can't find you, then someone's got to go upstairs and risk life and limb seeing if we can locate you. So don't leave and say, hey, I need to get home and take care of the dog. No, don't do that. You know, you won't, if the tornado hits you, your dog will never get you to take care of you, because you could be out of it, okay? So please, stay together. Now, once I've called roll, we've accounted for you, then if you want to mingle with friends, that's fine. But stay together until we get that done. Okay, so there's one emergency. External, weather. What's another potential emergency? This fire, exactly. Something inside the building. Not necessarily fire, it could be chemical spill. Anything inside the building that is potentially hazardous. Certainly a fire is the most likely. Chemical spill could happen. I can't think of many chemicals we have around here. But let's start with this supposition. Let's say my computer suddenly spontaneously combusts. Okay? It bursts into flames there. The battery goes bad. It starts smoking and belching flames and that kind of stuff. What do we do? Second? Okay. Okay, you exit and the room catches on fire and we're safe, but everybody else gets smoke inhalation. You know, come on, be a little more thoughtful than that. Okay. What else would we better do? If it initiates in this room, we are, say, smoke starts pouring out of the ventilation here. We're the first person to know about it. What else again?
Call 911.
Ah, very good. Okay. Now, actually, the very best is if you have the campus police number to put that into your phone. And let me see, I used to have it in here, and I hope this still works. I don't know if it still does. 426-3654. I was given that by Lieutenant Tate, who's the chief on this campus. I hope that works. 426-3654. You might want to put that in your phone in case anything comes up. That would be the best one. They will contact 911. But if you don't have that in your phone, 911 would be good. Okay, certainly that's one step. One other thing we ought to do, actually probably two. How will anybody else know the building's on fire?
Pull the fire.
Pull a fire alarm! Excellent! Where's the closest fire alarm? That's why we need to think about this ahead of time. Guess what? Everything you see on this diagram, somewhere around here is the midpoint of the building. This is the oldest part of the building here, and our part over here is second oldest, not long after that. The only reason I say that is the 200 start here and they go around this way, 250 start here and go around that way. So I think we must be a little bit nearer than that. Then, sometime later, this floor in here, this I call the nursing wing, some classrooms there, those were built. By the way, these numbers are first floor or second floor. These are the like 100 or 200s to 115 or something like that, 215, and from 250 or 150 up to around 260 or something, or 160 and 260 around there. Okay, in this area here, there's only one floor there. That's what I call the nursing wing, and those are the 170s. And I think one room goes up to 180. So these are the 170s in here. Okay? Now, since I've been here, this part in the middle here, which you don't see here because this is the first floor, this is the second floor, they don't have a second floor to it. But down on the first floor, this is what they call the student services floor. Okay, and those room numbers are the 180s and 190s. Okay? They don't have a second floor, but that's it. These are 170s over here, 180s and 190s over here. Okay? This part, that part, before they had requirements to have fire alarms. This is an old building. Don't go looking for fire alarms on any of these old halls that have the terrazzo floors. You won't find them. So the closest fire alarm, go out of the door here, take a left, go down this half flight of stairs. This time go down to that corridor and take a right, and as soon as you get in this is Student Financial Services right here. As soon as you get in that hallway, there's a fire alarm right there and one over here. Whichever is closest and easiest to get to, that's where the fire alarm. So one or two of you head out to get the fire alarm. One or two has already dialed 911 or the campus police. One other thing we ought to do, especially if the fire's in here, and I'll be mostly responsible for this, but you can actually help. What might we try to do? Put it out. How do we do that? Okay, where do we get water? Okay, something a little bit safer and closer than that. Fire extinguishers. Is that what you said? Okay, fire extinguishers. Where's the closest fire extinguisher? Oh, don't know that either. Okay. Where I'm standing about 5 feet from here, right there. You can't get much closer to the closest fire extinguisher. So yeah, I know you've always, if you were guys, I know this would be true. Gals, I bet. Always wanted to break that glass to see what it's like, right? Yes, okay. Break the glass. They have the tool there to do it. Give me the fire extinguisher. I'll try to get it put out. But one bad thing about water, if this was an electrical fire, you don't want to put water on electrical fire because water conducts electricity. You could get, or water conducts electricity, and there could be exposed wires. You could get shot from that, and it won't put out the fire anyway. Okay. Oil or grease fires. Water is the worst thing to put on that. It spreads it. Okay, so the fire extinguisher has a chemical in it, maybe carbon dioxide, whatever, but that would be good to put out the fire. Okay, now the paper on my desk, if that caught on fire, yeah, water would be fine on that. The wood and stuff, that would be fine. But you don't know if there's any other chemicals in there, so you may want to avoid that. Okay, so we've dialed 911, we pulled the fire alarm, we've done the fire extinguisher, and I'm in here to clear it. Now, what if it's not starting in here, okay? And you hear the fire alarm go off. What do we do there? That's where you were pulling in, right?
Exit go outside.
Okay, this time we exit the same way we did before, but this time we go outside, not inside. Okay? So you go out the door here, hang a left, go down the half flight of stairs, hang a left, go down the full flight of stairs, and when you get to the bottom, don't go in, go out. Okay? And you go out at least 75 feet away from the building. Okay, so head out of the door. I've got to get my orientation here. Here we are in this corner room back here. There's the stairwell. Go out there into the green grass here, and then keep on going till you get to the parking lot down there between this building and the next building. Okay? That's where they want us to be. Now, that's if there really was a fire. And what do you do then? Jump in the car and go, hey, if my building's on fire, we're not going to have any more classes today. I'm out of here. Right? Wrong. Okay? Because what you do, stay together in a group. Because guess what? It's going to be the last one out of the room. Me. I'm going to take my roll book with me and put out the fire if it started in here or whatever. And going to get out there and join you. And then I'm going to call roll again. And if we can't find you, if you jumped in your car and went home, and we don't know that, we have to assume you're back in the burning building. And so somebody, myself, a fire professional, somebody is going to risk their life and health coming back into the building, trying to find you when you have gone out to visit friends or taken off to go home. Don't do it until we've been together in a group, and then they say, okay, we're going to move our classes into these buildings, or we're going to dismiss for today, or whatever. Wait until you hear, and then act for it. But make sure you're accounted for. All right. Now, the last time we had a fire drill, and it's been a few years, a couple years, I think, they had us do something that I thought was really poor. They said, everybody go to the back parking lot. Well, that's not what you do. You don't practice on a fire drill wrong behavior. You got out of the closest exit. So I'm the only one, I think, that did. I took my students out of the right exit and then said, see that parking lot down there? That's where we would head if this is real. Where we're going now is to meet as a group and we're going to talk about it. So we went back up to the parking lot back here. But they had everybody in the whole building going out those doors in front, which is not what you do during a fire. So why practice wrong behavior? You go out the closest door, otherwise you may be going right past where the fire is. Not a good idea, you know. And you don't want to get a clog, you know, a bottleneck at one exit. You want it to be people out the quickest exit you can go to. Okay, so there's external weather, internal fire, or say chemical spill. What's one other safety thing we might need to consider? And back in the old days, I never thought of this. This is not the old days anymore. What happens way too frequently now? Say again?
Somebody come in.
Yes, active shooters. Okay? Now guess what? I'm hard of hearing. So the odds are, if there are some pop talks going on that you think could be gunshots, you notify me immediately. Okay? I may not hear them, I won't hear them as well as you do. So if you think that's the case, what do we do?
Lock the door.
Say again?
Lock the door. We don't have a door.
Lock the door. Excellent. Okay? I do have a key for this door. Now, this door does not have buttons here that you can press and lock it from the outside. I have to physically, and there's no keyhole in here. I have to physically go outside and lock this thing. Don't pull it too. Okay? I come back in, and now it's open from the inside, but locked from the outside. Okay? So, that's the first thing I do. Oh! Maybe one other thing, simultaneous with that. Call down 911, or even better, campus police if you got that in. If not, down 911. Tell them what you hear, where, your best location. Tell that. Do it quietly. Okay, you don't want to make a lot of noise. inside, but not on the inside of the office. That's not good. That means we can't get out, he can get in. Don't lock that door, okay? Now this door has keys and it has a deadbolt. Hey, that's good, except I don't have a key that works that deadbolt. So that's not good. We can't lock it anyway. This door, however, okay, now before you do, if you want to get up and see what I'm talking about, you can. Okay? You don't have to come over here so you can see. Okay? This one also has the button. This locks from the outside, but if we can get out, they can't get in. Okay? So this one we definitely want to do. But there's one more door here. I don't have a key for that. I want to close that door. And then get in here and lock this door. And then close this door. Why? He can see. Okay. I say he, most of the shooters have been he. Close this door so you can't see if anyone's in here. Okay. And why not go and close this door too? Okay. You don't have to. Okay, so we got that one locked, that one locked. Now what do we do? Ha ha! Get out of sight. In fact, get out of line of sight from the door. Because a powerful weapon can go through wood. It can't go through concrete block very well, can it? So we all get over here, get very quiet, and get so he can't see us. Turn off the lights. He comes by, the door is locked. Lights off, he hears nothing, sees nothing, he goes to another room. Yeah, not a bad idea to take those with you. Good idea. I hadn't even thought of that. Yeah, good idea to do that. Okay, and of course we dial 911 and we wait until we're certain that is a reliable source outside the door saying, "Is anyone in here?" You know, we don't want to open it for the shooter. We want to make sure. City police, something like this, you know. Campus police would be okay. And most of the time they'll have keys. And they'll come in and check. And if we know it's them, then we can leave with them. All right, I hate to go over that, but it's better to think about ahead of time than to not know what to do later. All right, any questions? Safety. Okay, good deal. Wow. Okay. Do y'all need a break before we get going on physical science? Up to you. Well, why is this not responding? Okay. Okay, I know none of you have your books right now, but I'll try to keep it sort of short and Swedish, okay, or Norwegian or something. All right, we're starting with chapter 14, the universe. First of the three sections on astronomy part. Now, sort of doing it kind of in what seems to me reverse order. We're starting with the universe, which is everything, and then we'll work our way down to the solar system in the next chapter, and then the Earth-Moon system, even smaller, in the next one. And then after that, we get to the Earth itself and deal with parts of it. And then we'll do the waters and weather and climate. So everything will be sort of geocentric from now. But the universe, big. Now, this is a beautiful picture, probably taken from the Hubble Space Telescope. And this is, we're going to talk about it later in this chapter, so you don't have to know this now, but this is probably the result of a supernova. And this thing in the middle here is probably a neutron star or white dwarf or something. What has happened here, some star has exploded. At the end of its life has exploded and sent the gases out in a big, and they call this a planetary nebula. Nebula means sort of nebulous cloud, you know, just a shapeless type thing. Planetary not means it's planets, but means it's going around something. So it's a planetary nebula. What's in the middle is the remains of that star, which is probably either a white dwarf or a neutron star or something like that. And that's in the center. This star will never be the star it once was. It just lost most of its material. Okay. The center is still there. It's still very hot. but it's not going to be there. Well, it's going to be there, but it won't even be bright after a few million years or so. Okay. So we're going to start with the universe and talk about concepts like that. What's the core concept here? We're going to talk about the night sky. Okay? This night sky is filled with, whether you can see them or not, billions of stars. Okay? And guess what the sun is? A very average, ordinary star. Average brightness, average size, average expected life. It's average in just about every way. It's not particularly hot, not particularly cool, average temperature, average just about everything. Why does it look so big and all those other stars look so small? Our proximity to it. And we'll talk about this a little bit later. But our sun is just an ordinary star with average brightness and just about average in every way. Now this picture is something else. This picture is taken on a very dark night where there aren't any external lights, and it's a camera that you just leave the shutter open on a very dark night, and no flashlights or anything else around, and just shine it fixed into space in the right direction. You point it to due north, the North Star, Polaris, okay? Pointing it to there and just let it sit, not moving or anything else. And basically what you see here, these concentric circles, those are other stars that seem to be going around the North Star. They're really not. They just look like they are. Okay? The North Star is this in the middle. It's not totally stationary. That's why it looks a little brighter there. That's the North Star, and then everything else seems like it revolves around it. That's looking at the night sky, time elapse. Okay? And we'll talk a little bit more about why that's true in this chapter. So let's start with the night sky. Now what we do, and we don't do it as well as they used to. Now we have a lot more tools and skills to do it with, but back in the old ancient days, they knew that night sky way better than we do. Because guess what? A lot of times they lived out there, okay? They were out there under that sky. And there was no cell phones and no TVs and no radios, nothing to be a diversion. So they just looked up and looked at those skies. And they saw sort of shapes in the sky. They saw patterns of stars. And they made up stories about them. Okay? They named them. Anyone know any of the names of those things up in the sky? We call them today constellations. Second, the Milky Way. Now, the Milky Way isn't really a constellation. It's actually a side view of the galaxy we're in. That Milky Way that you see, you won't see it much in town. You have to get out in the country somewhere where there's not a lot of other light. You can't see it on a cloudy night. You need one of those really clear nights. This time of year, there's really clear nights. You can go cold nights too, but you go spring or fall or even summer. Very clear night out in the country sometime, you'll see that pattern of, it looks like spilled milk going across the sky, and that's the edge of our Milky Way. What you're looking at is billions, if not hundreds of billions of stars that are so far away, but so close, not close together, but on top of each other. You don't see the individual stars, you just see the pattern of them. So yeah, that's one thing you could see. Okay? The constellations are what I was thinking of. Second? Big Dipper. Now, actually, the Big Dipper, when we go to the planetarium, he'll mention this. It's not really a constellation, it's part of a constellation. They have a name for it, I can't remember the name, but the Big Dipper is part of a constellation called Ursa Major. Ursa meaning bear, Major meaning big, so it's the Big Bear, and the Big Dipper is sort of the shoulder and one arm or something like that of the Big Bear, but it looks just like a dipper, okay? And so we call it the Big Dipper. We'll talk about that a little bit later. There's a smaller one, which is called the Little Dipper, okay? But that's part of the constellation Ursa Minor, the Little Bear. And you have have these two bears out there playing around. And those are related, and actually the end of the dipper, of the handle of the dipper, of the Little Dipper, is the North Star. And everything else goes around that North Star. So this won't be absolutely correct, but I'll just make up something and pretend it's correct. These things right in here would be the stars in the Little Dipper going around that end star, which is the North Star, and maybe this innermost circle here may be stars in the Big Dipper and other stars that are going around that. And then other stars and constellations are out there too. Okay? So there are two of the constellations, Ursa Major and Ursa Minor. Others include Pegasus, Orion, Perseus, Hercules, Cassiopeia. There's just a ton. I think the Greeks, most of these are Greek names and they're Greek mythology, legends, and things like this. So the people made up stories about them, and the guy over at the planetarium will usually tell a few of those. And they're really interesting. But they're just groups of stars that they are close together and they look like something. The one that I like best is Orion. Big Dipper is my favorite. Yeah. But Orion is next. That's actually a constellation, and it's it almost looks like the breastplates and the arms and the sword and the belt of a warrior. You know, you can't see a head or anything like that, but the rest of them, how do they get a bear out of that? You know, I don't know. You know, but they did, and I guess they had better imaginations. But why did the ancient civilizations know this? I already gave one reason. They didn't have any other distractions, so they just looked at the stars. But why else would they have known the stars in the night sky better than us? Second? Studied it. Yeah, because they had no other distractions. That's yeah. Why? What were some other factors here? Say again? Okay. They didn't have the light, actually what we call is light pollution. If you're in town, even Bessemer here, if you go out in the night sky here, you got lights in our parking lot, lights everywhere, street lights, car lights, building lights, all sorts of lights. Birmingham even worse. In fact, I grew up on a farm south of Augusta, Georgia. If you looked over to the north and a little bit west, I guess, maybe mostly north, you just saw a bright haze there. That was the city of Augusta. We were 25 miles away, and they're just all you saw. So if you're looking for some star in that, you're not going to see it. But out in the country, looking above where that light pollution wasn't bothering you, yeah, you could see more. Back in those days, no light pollution. They could see more stars, better stars, clearer stars, brighter stars, everything far better than we can. Okay? And that. But another thing. In some ways, their lives depended on studying those stars. Because just because it got a little warm, I mean, we may have this week or next close to 50 or 60 degree weather. Whereas last week we were 20s, teens, 30, yeah, awfully cold. Well, if someone said, well, we got 60 degree weather, is it time to plant? You know? You better not, because we're going to have more cold weather coming up. But see, we have calendars, we have clocks, we have cell phones, we have everything. Tell us what day, time, and stuff. They didn't. They had the stars, though. So they measured their seasons and lots of things by those stars. They knew if they were living in England when this star came up, when you first saw it the first time of the year, any time after that was good to plant. Because by the time you saw that, the chance of frost was over with. Now, just because you had a warm winter, don't go out there and plant early because you may still have a late frost. But once you saw that star come up, you were safe to plant. Okay? Those kind of things. Their lives basically revolved around the stars, you might say. Okay. So what are stars? Well, stars are those little prick. Now, are there any stars in the sky out there? You don't see any, but did any of you watch the solar eclipse last fall? Wasn't it fall? Yeah. And did you notice? Well, we weren't in the darkest part of it, but where it was a total eclipse, they could actually see some of the bright stars. The stars are out there. It's just our sun is the light pollution. Now, you're not going to see the stars because the sun is so bright, okay? But if the sun were to go out, like the moon coming in front of it, made the solar eclipse, then you could see some of those bright stars show up. They're there. You just don't see them, okay? But when you can see them, they appear as point sources. So even if you have a set of binoculars, they still look like a point source. If you have a telescope, they look like the point source. If you have the Hubble Space Telescope, the strongest, the most powerful, they still look like a point source because they're that far away. Okay? Now, we used to sing about twinkle, twinkle, little stars. Do they really twinkle? Not really. They look like they do because our atmosphere has variations in it, and that's what creates the twinkle effect. It's not the stars. Now, there are a few stars that they call variable density stars, or variable stars, and they do sort of change, but it's not in a twinkling kind of way. All right. Now, how close is the closest star? Well, even if you're talking about the sun is 93 million miles from us. That's 93,000,000,000. 93 million miles away. And that's our star. That's our closest star. That's that big old one we see out there. The next closest one is so much further away than that. It's measured in light years. You can measure it in miles or kilometers, but guess what? Those numbers are going to be astronomical. They're going to be so huge. So what is a light year? Well, it sounds like time, doesn't it? Is it time? No, it's distance. So what that means, okay, is light instantaneous? When you turn on the switch, the light is there almost immediately, right? So it almost appears like it's instantaneous. It's not. It travels at a certain speed. Now that speed is 128,000 miles a second. That's awfully fast. I mean, that's close enough to be instantaneous to me, okay? Let me see if I said that right. I should have that in my brain, but I don't usually remember things like that well. Speed of light, this is only in meters per second. I think that's right, about 128,000 miles per second. Okay? Now what does that mean? The Earth, is a huge globe, and that means light could travel, if it ran around in a circular path, which it usually doesn't, but if it did, it would go 4.5 times around the Earth in a single second. That's moving. That is awfully fast. But guess what? At 93 million miles away, the light we see from the sun actually left the sun a few seconds ago. Okay? Now, how far is a light year then? Light travels, let's say 100. Let's just say 128,000 miles per second. Multiply that by 60, and that's how far it travels in a minute. So now you're up to well over 1 million, okay, miles in a minute. Multiply that by another 60, and that gives you how many miles it travels in an hour. Now you're probably up pretty close to 100 million miles in an hour. And then multiply that by 24, and you have how many miles in a day? Well, now you're in the billions of miles in a day. And then multiply that by 365 and a quarter or so, and now you're a long way. Okay, that would be 9.5 times 10 to the 12th kilometers. So if you wanted that in miles, divide that by, multiply that by 0.6, you'd still be something on the neighborhood of, let's just say 6, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, miles away. Thousands, millions, billions, trillions, whatever falls that, okay? That's how far light travels in 1 year. 6 of those, okay? So guess what? We start measuring things in light years. 1 light year is that many kilometers. 9.5 times 10 to the 12 kilometers, or something around 6 times 10 to the 12 miles. That's enormous. The closest star is several light years away. In fact, I'd say several tens or hundreds of light years away. The closest star other than the sun. So you're talking distances that are just unbelievable. Okay? So those are what the stars are. What are your planets? Those are those little things that go around the stars, our sun, for instance. Now, the stars are producing their own light. The stars are incredibly hot. There are massive nuclear reactions going on. Our sun out there has massive nuclear reactions going on right now. I mean, bigger than all the atomic bombs that have ever been developed by man by factors of millions or trillions. I mean, just unbelievable amount of energy. They're producing their own heat and their own light. Planets do not. Planets are really cold bodies. Any heat they have, they get from the sun, okay? Or their own star. And any light you see is reflected light from the sun. Now, what's usually the brightest object you see? Not the sun, that's in the daytime. And at night, if the moon's out, that's the brightest object then. But after the sun and the moon, the next brightest object we see, in fact, usually it's the first thing you see when the sun goes down or the last thing you see before the sun comes up. We call it a star. It's really not. Anyone know what it is? It's two names or named stars, but it's not a star. In the evening, it's called the evening star, and in the morning, it's called the morning star. Pretty creative, right? And it's not a star at all. It's Venus. The closest planet to us, and it's still quite a ways away, a long, long ways away, more than 1 million miles away, but it's the closest one, and that's the first we see because it's closest to us and reflecting light from the sun. Okay? So planets are visible by reflected light. But when you look at them, even with binoculars, a good set of binoculars or a telescope, you see they're not just a point of light out there. You see it's actually a body out there, an extended source. And you sometimes see, remember when you look at the moon, sometimes the moon's a full moon, sometimes it's a half moon, sometimes it's a sliver, sometimes it's mostly a moon. Those are called the phases of the moon. You'll see the planets have phases too. Sometimes you look at Venus and it's just a little sliver. Not with your naked eye, it just looks like a star. But with a good set of binoculars or a telescope, looking at it, you'll see it actually, only part of it is lit. Okay, sometimes most of it is lit. Okay, that's what we mean by extended sources. You actually see the shapes of it. Okay, we'll talk about more of those later. But that's what a planet is. Now we can see a few other planets. The next closest planet to us is Mars. Now Mars is smaller, darker, so you don't see it nearly as easily as you see Venus. It's not a very bright planet at all. Okay? The next one is a huge planet, the biggest planet, Jupiter. And with your naked eye, you'll see Jupiter. Okay? But most of the time, not all the time, but most of the time it's going to be in the opposite direction of Venus. Because Venus is always between us and the sun. Jupiter is always on the other side of us from the sun. But occasionally it'll be lined up this way. But then you don't see it very well. You see it better when it's anyway, those are your planets. Saturn, I think you almost have to have telescope or binoculars to see Saturn. And Mercury is so close to the sun, you hardly ever will see it at all, because you only see it right at sunset or sunrise, and then you have too much light pollution from the sun, so it's hard to see. Just above the horizon and not always even visible. So most of the planets you're not going to see. Venus, Jupiter are the major ones. Mars to a certain extent. Now, what in the world is that picture? Anyone recognize it? It's not on some planet. It's on Earth. It is on a planet. It's on Earth. What is that? Anyone know?
Is it called Stonehenge?
Stonehenge, you got it exactly. That's Stonehenge. Now, there's other places that have sort of smaller versions of this, but this is Stonehenge. Well, old looking anyway, isn't it? And it is really ancient. We don't even know who built that. But that is not just a freak of nature. Someone built that. Okay? Now, it was so long ago, prehistoric, and yet they built that. Now, if I gave you the assignment to build me a Stonehenge, and by the way, let's see, I've seen some other pictures that show a person in here. If you saw a person, they would be about this tall. I mean, I don't see one in this one. They should have one in here just so you get it. These things are huge, monstrous. And how in the world did they do that? How did they put these great big rocks on top of two standing stones like this? And guess what? Those stones don't come from this area. They were brought in here from some other area. Geologically, they are not part of this area. So somehow they transported these huge hunks of things, and then they somehow got these up, they got them to stand up, and they got pieces on top. If I gave you an assignment, you would want to hire a crane, right? You know, you need some heavy duty equipment, bulldozers, things like this. They didn't have those. How in the world did these prehistoric people, whoever they were, get these to stand? Good question. But that's not the most amazing thing about it. If you stood in the middle of this circle of rocks, you can't really tell it's a circle, but stood in the middle of it, and then watched in the seasons of the year, a certain star is going to come up right in the center of each of those, telling you exactly what month it is, exactly what basically day it is. This is before calendars. They knew, and then they knew where they should be. They got them planted in exactly the right places. There are certain times when the sun comes up, it comes right through the slit and hits another slit. I mean, these are precise. Now, not only how did they get them there, how did they get them so perfectly arranged? I couldn't do that. With all I know, and with all, you know, the technology I have at my grasp, I would be hard pressed. In fact, any of us would be. Those ancient civilizations knew their night skies way better than we know ours. Most of us, anyway. There is something written at the top there. Oh, that's just copyright. See if I can find that in the book. Yeah, it's a slightly different figure in the book. Okay. Now let's introduce the concept of the celestial sphere. Now this comes from the ancient days, so this isn't quite accurate, but at least it's a good model. Okay? When those guys or gals were lying out in the night sky, looking up at the heavens, you know, on the ground, their bedroll at their head just looking up there, really the night sky looked like a big half of a bowl sitting above them, right? It started at the horizons and made its way to the top. So they considered it the celestial sphere. So the various objects on there, the moon, the planets, the stars and things, they were projected onto that sphere. they couldn't see this star is 17 million light years away, and this one's 5.2 million light years away, or this one's 85 light years. They couldn't say that. They all looked like they were on this big bulb that was up there, and they call that the celestial sphere. So it's just a model. It's not really what was done. But these objects are projected there onto some imaginary sphere surrounding the Earth. Now, if it surrounds the whole Earth, at any time we can only see half of it, right? So it's really a hemisphere, okay, because we can only see from the horizon up. We can't see from the horizon down, okay? Now, if you imagine the Earth in the middle of that, okay? So here's the Earth, and let's say we're right in the middle of that celestial sphere. Okay, I'm holding this, what I'm hoping is approximately level, and notice something a little unusual about the Earth there. Notice anything? It's tilted. If this is level, that's got a tilt to it. And if you were to measure this at the bottom, if this is 90 degrees, 80 degrees, 70 degrees, 70, if you go 3 degrees past that, that would be 66 or so. Basically, it's a tilt of about 23 and a half degrees. Now, I'm jumping way ahead, but that's what you see here. And directly above there would be Polaris, the North Star. Okay? Now, actually, I need to do something else to it. Let's turn Birmingham, Alabama around here. Okay, we really need to do it like this. So, Bessemer, Alabama. So Bessemer, Alabama is right up here, so the North Star is over there somewhere, directly above the North Pole. Okay, so what we're going to do is imagine we have a light in the middle of this, very bright light bulb. Okay, and most of this is transparent, but we're going to leave the equator on there, and that's going to get projected all around us here. Well, halfway around us anyway. So that projection of the equator from where we are in Bessemer, Alabama right here, that projection of the equator here is called the celestial equator, up on the celestial sphere. Okay? The North Pole will be somewhere up there. The South Pole will be below the horizon. We never see the South Pole. It's pointing down here somewhere, below the horizon, because we're in the Northern Hemisphere. If we were down in Sydney, Australia, which I heard last week had record high temperatures ever. There it is, Sydney, Australia. It'll see the South Pole, celestial South Pole here. It'll never see the celestial North Pole because it's pointing down here somewhere below the horizon. Okay? So, anyway, that would be the projection of our equator onto the celestial sphere. The North and South poles projected, and the Earth's equators and poles, they're projections of those. So that's going to be our basis. We're going to imagine on that celestial sphere where all those stars and things are out there. We're going to project the North Pole, which is a star, North Pole, and we'll project the equator there. So we'll have something to refer to. We can't see the South. Guess what? There is no South that's a South Polar star. We happen to have one that's really close to the North Pole. If you go to the South Pole, it's a big empty part of space. Not a star anywhere close. Okay, too bad. They don't have a South Pole star. Just that. Okay, well, let's see how that might look.
Question.
Yes?
So, down in down there where Australia is,
Yeah.
do they see the sky as we see the sky in the morning?
Okay, they will see probably a few stars we see. They will never see the North Star because it's below the horizon. They will never see the Big Dipper. They'll never see, certainly, the Little Dipper. They may see some of the constellations that are up here, we will see, and they will see. They'll be in different parts of the sky, but they'll see them. But, the orientation will be a lot different. But yeah, those around the equator, we all see. right up here at the North Pole, all you see, you don't see any south of the equator, only the ones that are above the equator. Because you never see the equator would be the horizon for you, okay? So, yeah, depending on where you are, you'll see some of the same stars. Certainly, a lot of things in the northern hemisphere will see mostly the same stars. Not all, but most. Okay, so here we have Earth in the center. And if you imagine a light bulb there, but everything else on the Earth is clear, right in the middle, then that would be the North Celestial Pole, the South Celestial Pole. There is actually a star on that one. There's no star down here. A lot of empty sky around it. And then this will be the projection of the celestial equator, which is not really anything there, but we just imagine it there. Okay? And that's your celestial sphere. Okay. Now, this is figure 14.1, which is the one we saw earlier. That's the North Pole or something in that, a time-lapse photograph of the stars apparently moving around the North Star. Do they really move around the North Star? No. North Star is there, the stars around it are where they are. They're all in the same relative location. What makes it seem like the stars are moving around the North Star? The Earth is spinning. So where we are now, the North Star is always in the same place, but these other stars seem to go, sometimes they're below the horizon, sometimes above the horizon. It's because of our motion, not the motion of the stars. But on the celestial sphere, it looks like they move. So how do we name those? Well, there's a lot of different ways they do. Okay? Let's say that I'm standing here and pick a star. Let's say this star right over there. You don't see a star, but let's just imagine this star right over there. It has two angles to it. One is called the altitude angle. From my horizon up to that star, that makes an angle, 20 degrees, say. Has another angle, and that's called the azimuth angle. Well, how are we going to determine that? Okay? Well, you can pick anything you want to. Let's say due south and go the number of angles from due south around to that one there. And what is that? Maybe 110 degrees. That would be its azimuth angle. Due north, it would be something else. Just pick some place and go from there. Okay? Now, there's another thing we usually refer to, and we refer to it a lot. It's called our celestial meridian. And what that is, if we face due north, and I'm hoping I'm facing pretty close to it, due north. Okay, pick the point just on the horizon, due north of us. Hey, thank you. Oh, you brought it by. Thank you so much. Due north of us. And go straight up until you're directly overhead and go around to due south. That's called our celestial meridian. Our own personal celestial meridian. Yours will be just a little off from that. No, that's your celestial meridian. Okay? That's the east-west location of the observer. Now, that's a rather strange way to say it. And it really doesn't make a lot of sense in this context, but that's what we are. Now, as we say, objects appear to rotate about the north axis. If you're in the northern hemisphere or the south, there's no south pole star, but they seem to turn around the south celestial pole there. That's because of our spinning, not because of their actually moving. Okay. So, she just saved me a trip. I was going to have to go to the Birmingham campus in the morning before class. Now I don't have to. Thank you very much, Miss Lewis. Okay. Now here we have the guy in the middle. This is us in the middle of that. And let's see, where is he looking now? I'm going to try to do what he said. Okay. If that's due south, he's going 45 degrees, okay. Now this is about 90 degrees, okay, 45 would be about there. And then go up 30 from our horizon, that would be a star right up there from due south. That would be its altitude angle, 30 degrees, azimuth angle from due south, 45 degrees east from due south. Okay? 0 would be north. Well, they chose these, but that's usually what you do. All right, now let's look at what you have. If your altitude on the horizon would be 0, 15 degrees, 30 degrees, 45 degrees, 60 degrees, 75 degrees, 90 degrees. So 90 degrees would be directly overhead. Okay. And by the way, we have a name for directly overhead. It's called our zenith. We'll talk about that later. Our zenith. And then we split that, anything along there, into those things. Now, that's a lot like our globe, isn't it? Our globe, we call the equator 0 degrees, either north or south, because it's right on there. And then you go up 15 degrees, 30 degrees, 45 degrees, 60 degrees, 75 degrees. Due north is 90 degrees. Due south is 90 degrees south. So we do our globe the same way we do this. And we don't have to use those. You could do 10, 20, 30, 40, 50, whatever. But, you know, those they did it in 15 degrees increments. Because there's exactly 6 of those between 0 and 90. Okay. I think we beat that to death, haven't we? Okay. Now, if y'all do need to take a break, let me know. I'll be glad to give you a break. I don't have to keep going forever. Okay. Whatever slide was there, they're missing it. Now, I'm afraid it may be the North Star thing. And I wish they had it. I think it's going to show up later. So I'll go ahead and skip it for now. But if not, we'll come back and look at that. Okay? All right. So now let's move on to stars. And by the way, let me just introduce you to a few things in the text. This text, they'll have something called a, not very often, science sketch. Draw a separate piece of paper or something like that, illustration of an observer standing near New York City, latitude 41 degrees, looking north at the North Star Polaris, you know, and go from there. I don't know. I don't find that very enlightening, but they like it. They also have things like concepts applied, okay? And I'm pretty sure he's going to talk about this when we go to the planetarium if we get to go. I'm so bad at names. And I've lost the roll. What did I do with the roll? Yeah. Oh, there it is. Hopefully. Yes. Okay. Rashandra, right? Rashandra was mentioning the Big Dipper, right? Now that is not quite a constellation, it's part of a constellation. They have another name for it, but it's so easy to pick out because it truly looks like a dipper. It has 4 stars that make the cup of the dipper, and then another 3 stars that make the handle from one of those. Okay, let's take the last 2 stars on that cup. The handle's here, the cup's there, the last 2 stars, the outer 2 stars on there. If you imagine a straight line through those 2 stars, going to the top of the cup, you might say the top of the dipper, and extend that into space, you're going to point to a very weak-looking, mild-looking star. That's the North Star. It's not a very big star, it's not a very bright star, but it's pointing to that. And then from there, and this is harder to see, those 7 stars that make the Big Dipper are really bright, distinct, easy to identify stars. They point to this little vague little dull star out there, and then if you look at that, you'll see a few more stars if you really have good imagination and good eyesight, and then another couple, and that's going to be the Little Dipper. Now the Little Dipper doesn't, the Big Dipper, the handle is curved right, everything looks good with it. The Little Dipper, it seems like it's sort of backwards. But the end star of the Little Dipper is the North Star. So the little bear just goes around the North Star. I don't know what part of the little bear that is, but anyway. So So anyway, there's the concepts applied. They're talking about the pointer stars at the end of the Dipper, part of the Big Dipper, pointing toward Polaris, which is the end of the handle of the Little Dipper. And if you got your text, when you see that, you'll see that. Okay, then the book has these things, which are sometimes pretty interesting and sometimes pretty weak. Myths, mistakes, and misunderstandings. The question is, can you see stars visible at the bottom of a well even in the daylight? Now, they used to think you could if you didn't have all that light pollution going on. Look down a deep well, it looks very dark down there. On the surface of the water, could you see stars down there? Theoretically, you might think you should. You never can. And that's what they're talking about there. So it's not a very important issue. But now moving on to 14.2, that's stars. Okay. Physical science? All right, good deal. Are you Gary or? Trey. Oh, you're Trey. Okay. Trey from last time? Okay. All right. I'm just not used to seeing you look like that. Okay. What's that? That's it. That's it. That's what happened. And let's see. Well, you weren't here for the first part, but you're here for the second part. I should have already called roll. By the way, remind me every time. I'm supposed to call roll again at 3 o'clock every time. So I'll get you in here. Alexis is still here, right? Mm-hmm. Let me, which is Alexis? You, okay. April was the one who left, or that you? I'm Miranda. Right, okay. So April had to leave. I don't know why. But Miranda's still here, and Trey just came in, and Rashonda's still here. Okay. Okay, so we still have 4. It's just not the same 4, but we've seen 5 so far. Now, for your benefit, Trey, right now we only have 7 paid students, because last night they removed all non-paid students from the roll. Now, if those other 4 students who were pre-registered but not registered don't show up by Thursday, I'm guessing there's a good chance they're going to cancel this class. Okay? I won't say so for sure. I talked with the other students, and I don't even remember if I did it after Rashonda came in, did I? I did, okay. If we had to cancel the class, would this mess you up for graduation or finishing on time? Could you still add another class? Because y'all are all paid, and that's still during drop ad. Thursday's still during drop ad. In fact, next Tuesday is still during drop ad, so you could wait till then, but I wouldn't. Would you be able to find another course? Would that mess you up too badly? Now, if we don't get the other 4 people to show up, then they may cancel the class, or at least 3 of them to show up. I think we need at least 10 paid students to run the class. So if we don't get them, they may cancel. But we're not going to make that call until Thursday. Okay? Can you do it, or would this mess you up big time? What's that?
I'd be able to find something.
You would, okay. And by the way, are you, I know Miranda is in my second mini-term class. Are you also scheduled for it? Or only this one? Okay. Well, second mini-term, if you don't have enough, it's almost the same time. It's the same days. It's just 1:15 to 5:45. The math, physical science 112 will be offered. So if nothing else, if you don't have anything that conflicts in the second mini-term with that, you could conceivably take that. You could just drop this and add that. That one has 18 paid students, so it's going to May. Miranda's one of them, and there's 17 others that are already paid, so that one's guaranteed to May. So if you wanted to, you could do that. But we're not going to make that yet. Okay. So let's look at the stars. Okay? What are stars? Now, even though they seem to be these tiny little points of light out there, they are massive. Some of the biggest objects in this world, in the universe. Okay? Believe it or not, they're gases, but they're very dense gases. Now, what do we mean by that? A dense gas doesn't make a lot of sense, because you think of gas as being not much there. but these are dense gases. That means you have a lot of molecules in that gas very, very, very close to each other, but it's still a gas. So very massive, very dense balls of incandescent gas. What does that word mean, incandescent? They're so hot they glow. An incandescent light bulb. What you do with an incandescent light bulb, you heat up that filament, usually tungsten or something like that, so hot that it gives off light. Okay? So that's what we mean incandescent. Okay? So these are enormous, massive, dense balls of very, very, very hot gases, so hot they're giving off light. What makes them so hot? They're powered by fusion reactions. Now, what do we mean by that? We have two basic kinds of nuclear reactions. The atomic bombs that we dropped over Nagasaki and Hiroshima at the end of World War II, and that most of the nations have done, like South Korea, North Korea, and others. There's only like 5, 6, 7 nuclear states that have mostly let off fission reaction. That's when you have these big, massive molecules. They're really not big, but compared to others, atoms, and they have so much mass in them, and you destabilize them, and they split apart. That's a fission reaction. Enormous amounts of energy are given off. But what a fusion reaction is, you have very small atoms that you force together real tightly, and they give off many times more energy than a fission reaction. That's a fusion reaction. So stars are powered by fusion reactions in their core. Now, most of what you see of the star, say the sun or something else, that's the outer part. The core is where those actually fusion reactions are happening. Really in the very, very center, but can you imagine just trillions upon trillions of atomic bombs going off at once, continuously? That's what's happening in the core of the sun. I mean, it's just unbelievable, okay? But the sun is just an average star. It's the reference for understanding other stars. Other stars are either brighter than the sun or dimmer than the sun. They're either hotter than the sun or cooler than the sun. They're either bigger than the sun or smaller than the sun. Our sun is really average in just about every way. Just about every way. So how in the world did these stars form? How did they get started? Well, out there in space, way out distant regions of space, okay, there are these masses of gases, just clouds of gases floating around out there. No real shape. They're called gaseous nebula, okay? The word we have, nebulous, meaning, not very well defined. Well, that's what a nebula is. It's just this mass of gases, okay? Huge masses of gases. Way bigger than our whole solar system, okay? Way bigger than that. Now, those gases are mostly hydrogen gas, the very lightest gas we have. Hydrogen has 1 proton, 1 electron, and that's all, folks. About 1 every 10,000 or so will have a proton, a neutron, and an electron. And maybe 1 out of every trillion have 1 proton, 2 neutrons, and an electron. But they're still the very lightest gases. Now, hydrogen is usually H2, 2 together. So even then you have 2 protons and 2 electrons, and that's all you got. 2 nuclei and 2 electrons. Lightest gas out there. And that's also what those gaseous nebula are. Now, periodically something happens. Now, it's hard to imagine what this something is, but I guess you've heard people talk about black holes, right? They are the most massive things we know about in all of creation, black holes. And there have actually been recorded times where 2 sure, particles or whatever. But if something like that happens, it doesn't have to be that major, if something like that happens, these shock waves emanate throughout these parts of the universe. So let's say these shock waves go and hit some of these gaseous nebulae, okay? I don't know if you realize it, but when I'm talking here, what I'm doing is I'm pumping air through my larynx, okay, if I'm pronouncing that right. And as I talk, if you hold your hand in front of your face when you're talking, you can feel little pulses of air hitting there. Well, that's a shock wave, you might say. It's a place where air molecules have been pushed together when my larynx was tight and forced air through it and they're compressed together. And other places where they're far apart. It's called condensations and rarefactions. And that's what's traveling to your ear. There's air molecules. It follows from my mouth. There's little waves of things. Compressions and rarefaction. Compression, rarefaction. So it hits your eardrum. And your eardrum responds to that and vibrates. And your nerves in there translate that into sound. So it's your fault I sound so bad. It's not me. No. Okay. So that's what a shock wave is. Okay. That's like a shock wave. That's some air molecules. Well, these shock waves from something out there in space go and hit these gaseous nebula and push some of them close together. Okay. And when they do that, okay, now these that are close together are attracted to each other because of gravity. Now, I don't know if you know what gravity is, actually. Any two masses that come in close proximity to each other are attracted to each other. Gravity is always an attractional force, and it always requires proximity. So what you need are masses and distance. And if the masses are close enough together, they're attracted. So this shock wave has pushed some of these gaseous nebula that are just out there floating around together, and it's pushed it close enough together, now they're attracted to each other. So they don't go back to where they were before. Okay? Well, as that happens, now they get more mass because there are more particles closer together. So they attract from further out and from further out. And they keep attracting more and more because the more of them they have, the more strength they have, and the more they do. That's called gravitational collapse. What was just a big mass of gases out here has now collapsed into form a ball of gases, you might say. Because the sphere is the smallest surface to collect that, and it keeps attracting more. You call that gravitational collapse. The volume collapses onto a very small volume. The gravitational energy released, you call that gravitational potential energy. That's where the front half of this book described all this, okay? We don't have the front half already done. Miranda will have it next mini-term. But these will be released into higher temperatures and pressures. Because guess what? If you bring more objects closer together, and guess what? These gases are always moving. I don't know if you've ever looked under a microscope just to see what's there. The things aren't still. They're always moving. The first guy to acknowledge that was called a guy named Brown. And they call that Brownian motion. These things are always moving, okay? And so you bring these molecules close together, and they're not static, they're moving. And as they're moving close together, what happens if you rub your hands together? They get hot, exactly, okay? So the gravitational energy is released into higher temperatures and higher pressures because now you have more molecules closer together. They have more weight per unit area. That's what a pressure is, mass per unit area. Well, now that you've got these pulling in more and more molecules, getting hotter and hotter and hotter, and it's mostly hydrogen gas, and that becomes a protostar, sort of like, I've heard it mentioned, a prototype. Someone's made an idea for a new car, a new plane, or a new something or another. They built a small model of it and call it a prototype. Well, this is a protostar. It's a small, before it becomes a star, it becomes a protostar, okay? Accumulation of gases that will ultimately become a star. Now that gaseous nebula may or may not ever become a star, but when it gets to this stage where it's gravitational collapse and it's It's going to keep drawing more gases in at some point. It's not a star yet, but it's past the Rubicon. It's going to become a star. That's a protostar. That's an accumulation of gases that will ultimately become a star. Okay? No backing off now. Okay? It will become a star. So, what happens? Well, the very core, it gets hotter and hotter and hotter, and because it's denser and denser and denser, still gases, but extraordinarily hot. And at some point, it gets so hot and so much pressure, so dense, that nuclear fusion happens. That these hydrogen atoms are pushed so tightly together, they now become helium atoms. Hydrogen with one proton each has become helium with 2 protons and 2 electrons. 2 hydrogens become 1 helium. Now, when that happens, you give off enormous quantities of heat. And this is in the form of gamma and X-ray radiation. Gamma radiation is some of the strongest radiation out there. You don't want to ever get hit by gamma radiation. Now, X radiation is pretty strong too. I bet you all of us have probably had X-rays before, right? Have you ever watched that technician when you are getting the X-ray? They leave out of there. They get behind a room, they go into a room like that, close the door, and if you've ever noticed that glass is very thick and very dark. And I guarantee you that wall that they're behind has lead in the middle of the wall, because they don't want that X radiation to do that. You're only in there for a few seconds and it gets you. They're in there all day long doing patient after patient after patient. Now that's for your mouth, that's for your bones, and for whatever. Those X-ray technicians have to get behind that wall, else their body gets exposed to too much of that and their body gets damaged. Because this high energy radiation is deadly. Okay? Guess what? The sun is spouting off this gamma and X radiation constantly. Why are we not toast? Second? Okay, yeah, but you see that the light gets to us, doesn't it? The X-ray and gamma radiation goes just as far, just as fast, just the same as light. Why are we not toast? Because it would kill us. Yes. Second? Okay, actually you're a real part of it. That's part of our atmosphere. We are surrounded by an atmosphere of gases, just like nebula gas. We're surrounded by an atmosphere, and in that atmosphere we have several other spheres of our atmosphere. Part of this is the ionosphere, and part of it is I think the ionosphere may be the one that contains the ozone. And the ozone's important, and lots of these other parts are to deflect that harmful gamma and X radiation. Not much of it ever makes its way through. Thank you, atmosphere. Could you live on Mercury? No. In addition to it being too hot in the day and too cold at night, it has no atmosphere to speak of. You would be completely incinerated by this gamma and X radiation. Okay? Venus? No, Venus has a much thicker, denser atmosphere than we do, but it's made up of carbon dioxide. And it's also made up of sulfuric acid and a lot of other things that you don't want to breathe, okay? So no other planet in our solar system has anywhere close to the particular type of atmosphere that we do that blocks those harmful, deadly gamma and X radiation. In fact, the only radiation our atmosphere allows through is that little visible spectrum of light, starting with infrared and going up to ultraviolet. Okay? In between there, red, yellow, orange, green, red, orange, yellow, green, blue, indigo, and violet. That little visible spectrum, that's most of what comes through. makes white light. Okay? Now, a little bit of infrared gets through, that's heat energy, and a little bit of ultraviolet gets through. Is ultraviolet good? No, not particularly. Okay? Ultraviolet is what causes skin cancers, sunburns, cataracts, wrinkles, aging. That's, in fact, probably why we die. Is because enough cells in our body get damaged by enough ultraviolet radiation over time that finally we quit working well. Okay? That's what causes skin cancers, like I said, and other things. So, thank you, atmosphere. But these are given off big time by the sun. So the fusion releases that, along with visible light and other things too. But the major things are those. Now, that's when fusion happens, incredible quantities of heat are given out. I mean, you're already getting all that heat from that got you up to fusion, but when fusion happens, I mean, that's would be like the difference between rubbing your hands together and trying to catch a ball of molten lead. You know, that no comparison. You know, so the pressure, friction, heat, that's hot, but nothing like what's given off when the fusion happens. So outside of that, let's see if we can get a figure here. Yeah. So that's happening only in the core. Ooh, it's hot. Okay. Innermost core, way, way, way in there is where the fusion happens. Then outside of this is called the radiation zone. Now that's still awfully hot, but what that is the radiation diffuses outward over billions of years. Remember that radiation is going at 128,000 miles per second, the speed of light, and this is such a big, whoa, this is amazing, okay? Radiating outward, okay? But gravity is pulling it inward, okay? So you have the fusion reaction before, when that was supposed to start, it was still collapsing, and it getting hotter and hotter. When it gets hot enough, then it explodes, basically. Fusion is happening, pushing things outward, but still you've got gravitational attraction pulling them inward, and that creates the equilibrium that you have. So the radiation is pouring outward, and then out here near the edge is still incredibly hot, but the radiation moving out cools off. When it cools off, it falls back in. This is called the convection zone, because that's what happens with convection. Did any of your moms or grandmoms or any of you, maybe you still have some of what they call divisionware, those pots and pans that you can actually see through? They were usually sort of amber colored. Ever seen that? Okay. We don't have any now, but I remember my mom had a set of them many years ago, decades ago. And you could actually watch water boil through because you could see through the pot. And in the very center, right over the hottest part of the eye, you'd see the water going up like this, and when it got to the surface, it cooled and it circled around, and it would just do this number, just like you see happening here. That happens in the outermost, and that outer shape then is what we call the surface of the star. But guess what? That surface of the star is not a solid surface, it's a gaseous surface. Okay. So the convection zone is structured by hot material rising from the interior, cooling, and then sinking back again. That's the convection zone on the outer part. The upper reaches create what we call the visible surface of the stars. Now that's the coolest part of the star. And look at what temperature it is. This is our sun, 5,800 K. Now what in the world is a K? Kelvin. It's a temperature scale. Okay? Okay? Okay. Now, you're probably most familiar with the Fahrenheit scale, right? Fahrenheit scale goes from 32 degrees Fahrenheit, which is the freezing point of water, that's where you start having ice and snow and that kind of stuff, to 212 degrees Fahrenheit, which is the boiling point of water. So we don't ever, we can exist down in this, but we don't want to do it for long. We never get close to this because our blister, that'd be way too hot for us. So we live within that range pretty much. On the Celsius scale, that's degrees C, that's 0 to 100. Okay, so basically it's the same general order of magnitude of Fahrenheit, but just a little bit smaller numbers, bigger degrees. Okay, what Kelvin is the same size degrees as a Celsius degree, which is about twice as big as a Fahrenheit degree, but same size degree there. But now you're going from a point 0 Celsius is as cold as you can ever go. Anything can, you can't go there, but anything can ever go. And here's how, I guess back, his name wasn't Kelvin, he was Lord Kelvin, that was his title. He was one of the few aristocracy that was also a brilliant scientist. That doesn't happen much. But he and others observed that when you cool a gas, the volume decreases, right? Have you ever had a basketball, football, volleyball, something like that, and you left it outside in the cold, and when you get it, it seems flat, but when you bring it in and it gets warmer, the sun shines on it and stuff, you don't add any air, but it becomes, its volume increases as it heats up, decreases when it cools, right? Well, they decided to plot a bunch of gases, or at least one gas, and they plotted the volume of the gas on the vertical scale, the temperature of the gas on the horizontal scale, okay? And as you cool it and cool it and cool it, the volume decreased and decreased and decreased. Now, somewhere down here, when it got very, very cold, then it went to a liquid, so it was no longer a gas. But for a long way there, it followed a linear trajectory. Well, let's do a different gas. They did a different gas, and they found out maybe it sloped like this, and a different one might be like this. But as they noticed, as you took all those different gases, no matter which one you were, if you extrapolated the lines past where they became liquids, they all pointed to the same point down here. That if you got to that temperature, the volume would collapse and be zero. Now we know that never happens. Okay? But theoretically, if it could, that's as cold as it could ever go. And the original line of thought, they thought all motion stopped then. Remember I said everything's always moving. They would think all motion stopped then. But we know it doesn't now. Quantum mechanics says it reaches minimum energy level, but it's still moving. But that's as cold as it can go. That's zero on the Kelvin scale. And we call it, don't ever call it degree either. It's 0K. 5,800 K. Celsius, Fahrenheit, you always have a little degree something. K, you never do. It's just 5,800 K. 0K. 500 K. 500 degrees Celsius, 500 degrees Fahrenheit, 500 K. Those are very different temperatures, by the way. But that's what a K is. Same size of degree as a Celsius, but it's coming from absolute zero. Okay? So that is really, really, really hot. But that's just average temperature for any old star. Our sun is an average star. About half the stars out there in the universe are way hotter than that. And about half of them out there are way cooler than that, or somewhat cooler than that. And then if you're in the radiation zone, the temperatures go up big time. When you're in the core, it's just unbelievable, the temperature. There may be a minimum temperature, 0K. There's not a maximum temperature. They seem like they just get hotter, 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 hotter. Okay. So that's our stellar modeling. Pretty good picture in the book. Now, the first example in the book, and I'm just going to talk about it a little bit. Remember I said one of my favorite constellations was one named Orion. The Orion Nebula, that's a nebula that's fairly close to the Orion. The Orion constellation, the stars may be incredible distance apart in different degrees and stuff, but from our viewpoint, it looks like it's one constellation. But somewhere out there in that is a nebula, a mass of gases, about 20 light years across.
that would be 20 times 10 to the 16 meters across. 16 meters across, which is an incredible. That would be 20, comma 000, comma 000, comma 0. Yeah, just lots of zeros there. Okay, which if you made it in kilometers, yeah, still lots of zeros. Enormous size. Okay. Enclosing roughly a spherical area about the volume, and they give you the volume there. And these are incredibly huge numbers. Calculate the approximate number of hydrogen atoms in the nebula, and then blah, blah, blah. So it's making a lot of assumptions here and basically just giving you exercise in dealing with big numbers. So I don't think it's really worth our time and effort to do, but what they're talking about, if that entire nebula, and they figure out how many atoms of hydrogen that is, a star like our sun was formed from approximately, and they give how many that is, and how many would you have? About 4,000 stars the size of our sun could come from that one mass of gases. Oh my word, that's an awful lot of stars, 4,000 of our suns. Okay. Would that ever happen? Probably not. Probably would form one star and maybe then another one later and stuff, but you don't form that many at once usually. The figure on page 14.6 is a photograph taken by the Hubble Space Telescope. Of that Orion Nebula, and it says it's the birthplace of an enormous number of stars. It could be up to 4,000. It hasn't made that many yet, ranging in size from the scorchingly hot blue giants to the tiny, dim brown dwarfs. Okay, many of the stars are hidden in the dense nest of the dust and gas, and you can't see it here, but that's an incredible picture. Like I said, it's not out there yet, but when I get Blackboard set up, if the class makes, I'll put some pictures. I'm not sure Orion Nebula is there, but some of the other nebulas where stars are being formed. They are incredible, incredible pictures. Okay. All right. I'm trying to see where they talk in the text about the lifetime of our sun, for instance. Okay, it's on page 357. I know you don't have your book, but those, when you get it, if you're listening to this, you can go back and get it. And the very figures here are in there. Our sun converts about 1.4 times 10 to the 17 kilograms of matter into energy every year. Now, wait a minute. Can you convert matter into energy? Is that possible? If I say the name Albert Einstein, what formula comes to mind? Oh, look at that. Okay. Now I'm going to set up my pen so I can write. Okay, let's go something sort of dark. Okay. So you just told me E equal mc squared, right? All right. Now, mass is measured in kilograms. Just to give you an idea, this text right here, now yours will be a little bit less than this. This text right here, I'm going to guess is about 1 kilogram. Okay? About 2.5 pounds, something like that. I think that's about right. It's about 1 kilogram of mass. Okay? 1.4 times 10 to the 17 would be 14, comma, 000, comma, 000, comma, 000. Oops, I did it wrong. next one or two up from there. I mean, enormous. That's how much every year that much mass is being converted into energy. So that's a huge amount of mass. Huge number. Now what is the C? What does that stand for? Speed of light. Speed of light. 186, I finally remember, 186,000 miles per second. 186,000 miles per second. Take that number and square it. Now you have about 12 places there, maybe more. Multiply that by this number, and you have an enormous number of amount of energy. That's how much energy has been put out by the sun every year. And every year it's taking about that many kilograms of matter. Now that's about 2,700 3-ton SUVs. That's how much matter is becoming energy every year from our sun. Now, our best guess, astronomers' best guess, is that our sun was born, that went through that process we talked about before, about 5 billion years ago. Okay? It's a long time. Enough hydrogen is left in our sun for about another 5 billion years. So not only is our sun an average star, we're right in the middle of its lifespan. Right smack in the middle. Now certainly we haven't been in existence that long, meaning the Earth, but not even the Earth, living beings. We've only been in existence just a tiny little fraction of that amount of time. So it was there, our Earth was there, lots of things were there, way longer than we've been here, and we'll probably be long gone before it ever uses that up. Now, the lifetime of other stars, so our sun has a lifetime of about 10 billion years. Okay? Other stars, the lifetime depends on the mass. Do you think bigger stars would have longer lifetimes or shorter lifetimes? Second? Yeah, you're right. Shorter. Because they're hotter and they're burning them more fast. You know, that much faster. Whereas the cooler stars, the less massive stars, are much cooler. They're not burning nearly as fast, even though they don't have as much to burn. I'm saying burn, but it's not really burn. It takes them a lot longer to do so. So the less massive stars will have longer lifetimes, as in trillions of years, whereas the most massive stars have very short lifetimes, only measured in millions of years, which seems pretty long to me, but it's not nearly billions or trillions. So the most massive stars have the shortest lifetimes. Okay. And they mentioned in the Orion galaxy, they are formed scorchingly hot blue giants, which are some of the biggest, hottest stars, to the very dim brown dwarfs, which are the coolest, smallest stars, whereas the big ones are going to disappear in a few million years, completely explode, whereas the brown dwarfs will be around for trillions of years before they end their lives. Okay. Now let's look at the brightness of stars. This is on page 358. Okay? Now, there's several ways to talk about the brightness of stars. But the amount of the brightness, differences in their stellar brightness, depends on three major quantities. The first is how much light is produced by the star. That's a function of temperature. How hot is that star? So how much light is it actually producing? Another thing is the size of the star. A bigger star is going to appear much brighter, even though it may be cooler than a small star, because it's just so much bigger. But the major one is how far we are from the star. We're so close to our sun, it's by far the brightest star we see. But it's not the brightest star in the sky. It's on the average, very average. Many of them are much bigger than the sun, some are much smaller than the sun. Many produce more light, many produce less light, but because we're so close to it, it looks enormously brighter to us. So the first way we're going to look at this is the apparent magnitude of the brightness. This is a scheme to quantify the observed brightness just by what we see sitting here on planet Earth. The first magnitude stars are 100 times brighter than the sixth magnitude star. 5 uniform divisions in between. So first magnitude, let's say, is 1. The sixth is 6. So in between you have 2, 3, 4, 5. Okay, 5 uniform divisions in between those orders. Now here's the scale that illustrates that. Here's apparent magnitude, and what we're going to do from the faintest star that can be seen by the naked eye, that's going to be, looks like about +6. No. Okay, let's see. Yeah. No, that would be the, yeah, that would be the 6th order magnitude. Okay. Up to the brightest star that we see in the sky, not counting our sun, the brightest star in the sun, that in the sky that we see is Sirius. Are you serious? No, this is spelled S-I-R-I-U-S. I think that's like the music that you pick up on the internet. Isn't that the Sirius channel or something like that? That's how it's spelled. That's what they named it after. There are 6 orders of magnitude here. The first magnitude star, that would be Sirius, 100 times brighter than the 6th magnitude star, which is the faintest star that you can see with the naked eye. Okay. Now, just to get a perspective here, those are the stars. These are the ones you see. Jupiter is brighter than even Sirius. Jupiter's not a star, though, it's a planet. What we're seeing is reflected light off the sun. Sirius, you're seeing light coming off Sirius, okay? The brightest Venus is even brighter than Jupiter, okay? So it's up here, looks like maybe about -3. Now, for some reason, the brightness numbers, as they go negative, they get brighter. Who made up this? I don't know. And pluses are getting dimmer, okay? Ugh. So Venus is something around 3 maybe. The full moon is up there around 11 or 12, -11 or 12, and the sun is up there around -26, okay? So that bleeds out everything. You can't see any of these other things. You can see a little bit of a full moon, not much, when the sun is out, but because the full moon's on the opposite side, obviously we usually don't see that very often. Okay, so these are the ones we see. Brightest actual star is Sirius. The Andromeda Galaxy, which is not really a star, but it's just about in the middle of that, maybe about +4. That's actually part of the Andromeda constellation, which the galaxy got its name from, because what appears to be a star in that is actually a whole galaxy, okay? Billions and trillions of stars, okay? Now, if you have a great set of binoculars with the naked eye, you can go up to about +10 or 11. Pluto, at its very brightest, is +15. You'll never see Pluto with a set of binoculars, ever. You need a very powerful telescope. And the naked eye with a very large telescope will see up to about +18 or 19. So what we see with the naked eye is between 0 and +6. The stars we see, and other things can be brighter. Okay? That's apparent magnitude. Now, is Sirius producing the most light? Probably not. Is it the biggest? Probably not. It may be closer to us than some of the others. Okay? some of the other bright stars actually may be producing a whole lot of light. Maybe Sirius is too. It's just hard to tell because all these three factors work together. So that's apparent magnitude. Well, that's not a very good thing to go on. We need absolute magnitude. Now you might be wondering, who cares what these magnitudes are? We do. We just don't know we do, okay? The next slide or two after this, or it might even be into Thursdays, we'll see why we worry about this. So let's do another way of looking at magnitude. Absolute magnitude. That's the brightness adjusted to a defined standard distance. So in other words, the very hottest stars are going to be the very brightest stars, and the cooler stars are going to be not so bright. And our sun's going to be right about in the middle. So our sun, which the apparent magnitude was about negative 26.7, on absolute magnitude, is going to be at plus 4.8. Boy, that went down really big time. And remember, the range being from 0 to 6, this is actually closer to the 6 than it is to the 0. So it's not really one of the brightest stars out there. Now, they throw in another term here. That term is luminosity. Total energy radiated into space per second. It's directly related to the absolute magnitude. How much light is actually being produced, given off into space from that star, related to the absolute magnitude. Now, we're going to correlate those units to the sun, and we'll say this 4.8 sun, our sun out here, 4.8, is going to be 1 solar luminosity. So Sirius is probably going to be way bigger than that, and then some of the smaller ones are going to be way less than that. Okay? So that's our luminosity related to absolute magnitude. Well, we still don't know why we even mentioned those. We will. We'll get to it. Now we're going to jump another rabbit, and this is sort of related, but not directly. What's the star temperature? Okay. The color variations are apparent to us. You have red stars, yellow stars, and bluish white stars. Which of these do you think would be the hottest? Red, yellow, or bluish white? Second? The bluish white. You're absolutely right. Any of you have gas cooktops at your home as opposed to electric? You have gas? We do too, yeah. What is the flame there? Blue. Okay. Red, that you usually think of hot, that's the coolest temperature. Okay. It's hot, but it's not nearly as hot as a blue. Okay. So yellow is hotter than red. So the color is related to the surface temperature. Now we measure this or determine this by what we call black body radiation curves, which is a big mouthful. The red are your coolest stars, the blue are your hottest stars. And guess what's in between? Yellow, and guess whose star is yellow? Ours. The good old sun is right in the middle, average star. Now, the classification scheme here is based on temperature, and hottest to coolest, the brightest bluish whitest star are your O stars, followed by the B, which sounds bluish, and the A, or even sort of in the blue. Then you get down into the yellow range of your F's and G's, and then the red range of your K's and M's. We are a G star. We're on the lower end of the average yellow stars. Okay? Now, here's those black body radiation curves. Okay? Just a little bit of definition here. Usually the longer the wavelength, the less energy it has. It sounds sort of inconsistent, but it's true. Because wavelength is inversely proportional to frequency, and the higher the frequency, the higher the energy. So the larger the wavelength, the lower the energy, because the lower the frequency. So these are the coolest down here of the I said it backwards. Coolest up here, hottest down here. Because longest wavelength, coolest, shortest wavelength, hottest. Okay? Now, if your average is in the red range down here, those are your coolest stars. If your average is in the green to yellow, and we're in the yellow, because we're 5,800, this is 6,000, this is surface temperature of the stars, then this is your average stars. That's where we are. Okay? And the very hottest stars are up here in the blue-white, actually almost violet or purplish kind of stage. That's up to 10,000. Boy, those are hot stars. Hot. Okay? Now, on the lower end below red is infrared. That's basically heat energy. Okay? Above this is the ultraviolet, which our atmosphere blocks most of, but it doesn't block it all. And that's why we get sunburns, skin cancers, because ultraviolet is harmful radiation. Now, and hopefully you will when you get old enough, you'll think about it more. When you're out in the sun, you really should have sunglasses, but not just any dark sunglasses. Good, you need that that's UV rated, and they have UVA and UVB. You need them both. Okay, there's different levels of ultraviolet radiation. You want sunglasses that will block the ultraviolet radiation, because that's what does the damage. Not necessarily the darker glasses, though they are usually quite dark, but you want those that are UV protected. And same thing for sunblocks. You want UVA and UVB, not just something. Okay, so these would be your O's, your B's, your A's, your F's, your G's, your K's, and your L's. Okay, that's to measure that. All right, they had example 14.2 here. The brightest star in the Earth sky, night sky, is Sirius. And Sirius has an absolute magnitude of plus 1.4. Okay? Now, our sun, remember, was 4.8. Okay? So 1.4 is going to be a much hotter star than our sun is. Okay? Way much hotter. Now, don't worry about this. This is on. Okay. Yeah. That is apparent magnitude. This is the absolute magnitude. So Sirius is much hotter. Tells us that Sirius gives off more light than our sun. How many times brighter is Sirius than our sun? And you can look at those ratios here. And they give you a formula. Equation 14.1, I would say don't worry about it. It's an exponential equation. And if I tell you that the math level for this course is around 98 to 100, you haven't even gotten close to the exponential notation in that thing. So we're not going to worry about that, but if you do follow it, you can read that, and it's a pretty interesting exercise to look at. Okay? So that would be about 4 times brighter. I'm sorry. Each point there. Okay. And then luminosity is mentioned there too. Now we've hit star temperature, which was this slide, and your black body radiation curves. Okay. Here is a table. Does this show up in your yeah. Where it's brownish looking here, this is your sort of a greenish table on page 360 in your text, table 14.2. Okay? And this shows these letters down here and what they correspond to. The type O stars, they are definitely bluish white. Very hot. Their average temperatures vary from 30,000 K to 80,000 K. Now, what are they made up of? the spectrum with ionized helium and hydrogen, little L's. These are very short-lived, very rare stars. They don't hang around very long, only millions of years or less. Very, very short, very rare. That kind of temperature, they're burning their fuel. They're fusing the hydrogen so incredibly quickly. But you don't even have normal hydrogen existent that is such a hot star they're ionized. Now, what's the difference in an atom and an ion? Does anyone know?
It has to do with the electrons. It either has extra, more than one electron.
Okay, got it. Okay, an ion is an unbalanced atom. Atoms, okay, like I said, hydrogen is one proton, one electron. Okay? Now, hydrogen very seldom will pick up an electron. It may lose an electron, then it becomes +1 charge. That's an ion, hydrogen ion as opposed to a hydrogen atom. So it's either gaining or losing an electron, or one or more electrons. So here, you don't have any neutral hydrogen or helium. They're all ionized at such incredibly high temperatures, your electrons are fleeing, and moving around. So they're not, you don't have atoms of hydrogen and helium, you have ions of it. Your B is the next hottest, and that's bluish, 10,000 to 30,000. The spectrum with neutral helium, none of it ionized. So it's all ionized only at the O level. So that's what distinguishes. A is also bluish white, and this is 7,500 to 10,000 K. Spectrum has no helium, strongest hydrogen, some magnesium, and calcium, which to me is a little bit surprising, but I guess not too surprising. Okay, the F is the white stars. I said that wrong before. I said that at the beginning of the yellow. This is actually the white stars, and these are 6,000 to 7,500 K. The spectrum with ionized calcium, magnesium, neutral atoms of iron. Not too surprising, iron pops up in there. The G star is the yellow star. That's where our sun lives, 5,000 to 6,000 K. We're at 5,800. The spectral type of our sun, the spectra show 67 of the elements in the sun. Okay? Now, hopefully when you get your books, they will have the periodic table. They may not have it on the back inside cover, but somewhere near the back you'll have the periodic table. I asked them to put it in there. First time they did the customized text, they didn't put the inside and they didn't put this inside. So I specifically asked them to, so they did. 67 elements, basically it goes from helium through approximately holmium, which I don't see much of that anywhere either. So basically it has all the first row, second row, third row, fourth row, fifth row, the start of the sixth row, and a little bit, most of the sixth, a good portion of the sixth row. The heavier ones down here don't show up in the sun. They just haven't, it's just too hot for them to form, I guess. I don't know. Okay. Orange red, you're getting down in the K stars here, 3,500 to 5,000 K, spectrum packed with lines of neutral metals. Okay, so you have lots of those metals in the middle of the table, and they're neutral. There's no ionization. The M are the reddish stars, 2,000 to 3,500 K, bands of molecules, not just atoms or ions anymore. Now you have molecules, titanium oxide, and there's a lot of verbiage there that without having read earlier chapters, it really doesn't make a lot of sense, but there's what you got there. All right, so now we have star temperature. We have absolute magnitude and star temperature. Why did we come up with these? Here's why.
couple of guys, one named Hertzsprung and the other named Russell. I'm pretty sure Russell was American. I'm not absolutely sure. I'm guessing Hertzsprung may have been German or something. But anyway, there's a couple people. If you chose to write on people, a couple of them right there. They came up and formed this diagram. Now, this diagram is kind of an artificial type thing, but what it did, they just plotted stars with their absolute magnitude on the vertical scale and the spectral type, the O, B, A, F, G, K, M, on the horizontal scale. And when they did this and matched up, the stars that had this spectral and that magnitude of this, they found out the stars naturally grouped together. Now, this is not spatial. This is not out in space. You don't see stars like this. But when you plotted them, this is what they became. The ones down here are white dwarfs. These are white, meaning they're very hot. They can be very hot, but they're very small stars, so that makes the magnitude, absolute magnitude, pretty small. It's a high number, but that means a low magnitude. Okay? These are what's left over when a star has died. These white dwarfs. You can still see them. They're bright enough, but they're small. Can be quite hot. Okay? That's that. The main sequence stars are the stars in their normal lifespan. Our sun, guess where? Right in the middle. Okay? Not too much this way or this way, this way or that way. Right in the middle. Remember, it was about 4.8. There it is, between 0 and 5, 4.8 this way. And what was it? G down here? Yeah, a little bit on the low side of G. There we are. The sun, right in the middle. Now, on the other side, we have cooler stars because they're on this side, but they're huge stars. They're giants. So that gives them a pretty good absolute magnitude. They're not that hot, but they're big enough to have a large magnitude. And these are the giants here, and sometimes they're called red giants because they're down almost in the red range here. These are stars on their way out. Before they become white dwarfs, but they're not quite there yet, but they're getting there. Now these are the supergiants. Now some of these can be quite hot, down to quite cold, but they're huge, massive stars. These are the ones that are so big, they still have a lot of heat in them, but they're so big, there's very large absolute magnitude. A small number, but very easy to see. Okay? These stars, when they end, these are going to be the supernovas that are going to produce mostly black holes. Maybe neutron stars and black holes. These will only produce white dwarfs. And then it's best. Okay, we'll get to that part a little bit later. But notice they group themselves when you use these, and that's why we brought up absolute magnitude and spectral types, because when you use these as your markers, your stars group this way. Now, remember we said the brightest star was which one? Sirius. Are you serious? Yeah. Okay. Now, Sirius is actually a binary star. Most stars are binary stars. Our sun is one of the rare ones that's not a binary star. Sirius actually has one main sequence star paired with one white dwarf. Okay? So it's actually a binary star of two stars that are gravitationally connected to each other. They rotate around each other. This is a normal star, not that, it's, like we said before, it's a 1.4 magnitude or something about like that. But it's paired with this one, so it makes it a little bit brighter. But it's not all that hot of a star. It's in the main sequence, but its sister star is already on its way out. It's a white dwarf. Can be pretty hot, but it's very small, so it doesn't
any of these that you see A and B, like Procyon A and Procyon B, I think we'll see that in the lab maybe. We'll see Sirius in the lab. I think we'll see Vega in the lab. It doesn't say it's a, now this could be a binary star, but they're both main sequence, so they're not split up. Regulus, I don't remember seeing that in the lab. Procyon, I think we did. Pollux is a giant, but a cool one. Arcturus, Aldebaran, pretty big, noticeable star. Antares is one of the big ones out there. Betelgeuse is. Rigel is. I think we see that one in the lab. Okay. And he may point out some of these when we get to the planetarium. Sometimes he does, sometimes he doesn't. But that's why we introduced the concept of magnitude, apparent, then absolute, and then spectral type based on temperatures. And that groups our stars into these things. All right. Now there's another little science sketch here. Oh, there was another example. I didn't want to skip over it. Let's just take a look at it. What is the temperature of a star emitting light with a peak wavelength of 3,500 angstroms? Okay. Now, you can do the math. They give you another formula there that relates temperature to wavelength, and that's basically coming off of here. So if we look at this, 3,500 angstroms, that's the wavelength. That would be somewhere about in here. So that looks like its temperature would be up around 10, greater than 10,000, and sure enough, it's 830,000. So, no. Yeah, 8,300. Okay. So, not quite up to 10,000. So, you can sort of pick that out of the table, but the formula gives it to you exactly. Okay. Don't want to get onto that too much. Okay. If you like working with stuff like that, knock yourself out. Okay, concepts applied, seeing the spectra. I'll ask you why, I think. They talk about some things you can get to play around with. If you're interested in that, go for it. All right, here's one thing. I do want to mention this because it does show up somewhere. I can't remember where. Before we get to the life of a star, which is the next slide, that slide. Before we get there, let's go back to this one. Now these do not show up on the Hirschsprung Russell diagram. That's what that is. But they mention them here as if they do. Stars such as the sun emit a steady stream of light, because the force of the gravitational contraction is balanced by the outward force of the, they say energy, but that's the fusion explosion. You know, the radiation outward is balanced by the gravitational contraction. There are other stars called variable stars. They're stars that change in brightness over a period of time. One of these is called the Cepheid. I don't know if that's the correct pronunciation of it. Variable star, slowly changing variable star that is used to measure distances. Okay. General relationship between the period and the brightness, and it tells a little bit about that. So this is what the guy named Hubble, who would be a very good guy to look at, one of the greatest astronomers, most contributions that we've had. He used these to estimate distances. So I'll let you read that, but I did want to point that out. Oh, there it is. I'm sorry, I knew it was somewhere here. I just didn't go through this enough. I looked at the diagram but didn't do this. The Hertzsprung is a plot of absolute magnitude vertically versus stellar temperature, which is your spectral type horizontally. Each dot represents a star. Now these don't mean they're close to each other in space or anything. They're on this diagram. The characteristics of main sequence stars is the purple eel in the middle, okay? The red giants are the blue stars, just called giants there. The novas are the supergiants that are going to ultimately become supernovas. The white dwarfs are the ones down here, and super variables. Where in the world is this? I don't know. It's not on the diagram here. These are standard stars for distance calibration, and that was Hubble telescope. I mean Hubble, who they named the telescope actually. Edwin Hubble, big name in astronomy. Okay. So let's look at the life of a star. This doesn't mean a musical genius or anything like that. Okay. The protostar stage. Remember, that's the early part when the gravitational contraction is happening and they're building up temperature. Gravitational collapse, the density, temperature, and pressures are all increasing big time. When you reach a temperature with that gravitational collapse of up to around 10 million K, whoa, that's hot. That's when fusion ignition temperature. That's when hydrogen starts fusing into helium. And when that happens, way more energy is given off. That makes this ring really small. And then you form what you call your dynamical equilibrium. Now, this is sort of a strange expression. Equilibrium means almost things are equal, okay? But dynamical means they're changing, okay? So it's not just that it's equal, but it's a moving equal, okay? So you've got gravitational collapse pulling things inward and the fusion expansion pushing them outward. And when that settles out, you have sort of your standard dynamical equilibrium. Now, what I'm guessing a Cepheid variable is, it's not quite a stable equilibrium. It fluctuates, okay? And that's what gives you a way to measure distance, okay? So the dynamical equilibrium, the inward force of gravity, balanced by the outward pressure of the fusion energy pushing out. When that is obtained, when that's reached, after the protostar stage ultimately is going to become a star. Once that is reached, then you have a star in the main sequence. Okay? So maybe those Cepheid variables are new stars that haven't quite reached this yet, and that's what we're measuring. They aren't real clear on where they fall here, but that would kind of make sense. Whether it's true or not, I don't know, but it kind of makes sense. Okay. So here's kind of what we have happening here. The inward force of gravitational collapse, but the outward force of the expansion from the nuclear fusion reaction. Pushing outward, gravitational pulling inward. This now, and all of that is happening, all the fusion is happening in the core only. And then, so this isn't quite the same diagram as before, but this explains the forces of that diagram. Inward force due to gravity, outward force due to the fusion explosions. And when this is balanced, you have the dynamical equilibrium. Now it's a star in the main sequence. Okay. So that's protostar is the birth. This is the normal life. This is the stable life of the star. This is the 10 billion years of the sun. Trillions of years for the low temperature stars. Millions of years for the high temperature stars. They're in that stable equilibrium, dynamical equilibrium. What happens from there? Okay, so you are also tracing the path across the HR, that's Hertzsprung-Russell diagram. Now,
what happens, you know, remember they talked about the sun. The sun has been fusing hydrogen into helium for about 5 billion years. They think there's enough hydrogen there, studying the spectral and stuff like that, for another 5 billion years. When that starts near the end of that next 5 billion years, I don't think I'll be around then, okay? But I don't think mankind will be around then. The hydrogen will, in the core, basically gets exhausted. You've used it all up. What happens? Well, remember the fusion was blowing things outward. When you don't have enough fusion happening, now the core collapses. When it collapses, okay, it's already hot, really, really hot because of the fusion. Now when it collapses on itself, it heats up even more. I mean, big time heating up. Now this is the core. When the core heats up even more, the outer shell expands. Because the outer shell, remember, is not where fusion was happening. This is the radiation zone and the convection zone. This is expanding now because of the heat in the core, but when it expands that much and no new fusion happening, it's cooling. And as it cools, it drops in its spectral type from, say, blue or yellow or whatever down to red. Okay? So when it cools, it becomes that. Now, again, we mentioned this earlier, the O stars, those very hottest stars, will live for only millions of years. The M stars, the very coolest stars, will go for trillions of years. We're in between that. We're a G star and go for about 10 billion years. The mass determines the ultimate fate of the star. Not only does it determine how long it takes to get there, it determines what that fate is. And here are some explanations of that. Now this is your star. Picture your Hertzsprung-Russell diagram. Here's the purple snake in the middle. That's your main sequence. That's where it starts as a 1. And when it uses up its hydrogen and collapses and heats up and blows out the thing, now it gets much larger in size, but begins to get much cooler in temperature. So this becomes what they call the red giants. Okay? Now, depending on how hot you are, that could become super big and become a super giant or whatever, but anyway, once it collapses, it can go down here and become a white dwarf. Okay? So, white dwarfs are still pretty hot. They were cooler there. We haven't gotten to that yet. We'll get to this later. Right now, we're just in this phrase here. Cooling off, and the mass determines the ultimate fate of the stars. Let's get there and see what happens. Okay. Late in the red giant stage, that's somewhere up here, further core collapse. It just continues collapsing, but the core is getting hotter now. As it collapses, it gets hotter. If it gets hot enough, and most of the time it will, now you go not to hydrogen fusing to helium. By the way, on the periodic table, which will be in your books, hydrogen's here, fuses together to form helium. Now you have helium fusing together, and it forms carbon. Because helium has 2 protons, 2 neutrons, fusing together to become carbon, which has 6 protons, 6 neutrons. Now, it doesn't sound like that adds up right, except if you think 3 heliums combined to make 1 carbon. So that's a sort of a triple fusion. So when that happens, suddenly you have radiation energy again. So the radius and the luminosity, the radius, this is bizarre here, the radius and the luminosity decrease, it moves back to main sequence. Okay? When you go after the red giant stage, you go back into a main sequence star because you have fusion going on again. It's not hydrogen fusing to helium, it's helium fusing to carbon. Okay? Now, let's go
go to the end, the less massive stars. The helium fuel in the core is used up. That's used up pretty quickly because remember, 2 hydrogens make 1 helium, but it takes 3 heliums to make 1 carbon, so you don't have as much of that to happen. So after a while, that is used up. So the helium and the hydrogen fusion themselves are completely exhausted. The instabilities, okay, so what you have here, this is grouping a lot of things together. You have a rapid collapse now, and that heats up and blows off the outer layers of the gases in those outer layers. Remember that planetary nebula we saw at the beginning? You had a little thing in the middle, and your gases out here. Very, like, second, third slide we saw in the whole slideshow, that was a planetary nebula. The center of that is a carbon core, okay, contracted to a white dwarf, and over time, it's white because it's so hot, but over time there's no new fusion, so ultimately it cools off and just becomes a black lump of carbon. Now, when I hear black lump of carbon, I think a piece of charcoal or coal or soot. But when they say black, they mean it's not emitting any light. White would mean it's emitting light. Black means it's not emitting light. Now, actually, one of the first, it's going to end on a silly note here, but actually, from what I understand, it's true. It became, where did they say? I guess it was on the previous slide. It became a white dwarf. That is, that carbon fusion is happening. And when carbon, under very high temperatures and very high pressures, what does carbon become? Say it again? Diamond. Okay? Now, the first of these white dwarfs that they detected, the astronomers, physicists are sort of crazy people, they named that first one they found. Anyone know what they named it? Lucy. Now, why would they name a white dwarf Lucy? This was back probably in the 60s, 1960s, when one of the most popular singing groups on the planet was the Beatles. And some of these astronomers must have been Beatle fans. And one of the Beatles' old songs was Lucy in the Sky with Diamonds. Ever heard of it? Sounded a lot better than that, by the way. You never have heard of it? Really? None of you are Beatles fans, huh? Y'all even know who the Beatles were, do you? Oh, you do. Check it out. That was one of their songs, and what would a lump of carbon be under high temperatures and pressure? Had to have some diamond in it. And guess what? That was left floating around in the atmosphere, not atmosphere, in the galaxy. And then when some new star was formed and blew things out, little traces of diamond may have got distributed to various planets, and maybe that's what our diamonds are. They may not just be from compressed carbon that we made from plants and stuff. It may actually be those remnants of a star many millennia ago. Okay, so that's what happens to the less massive stars. It becomes a white dwarf, and then it cools. Oh, there's the white dwarf. I knew it was somewhere out there. And cools to a black lump of carbon. Black doesn't mean the color of it. Black means it's emitting no light. It could be black diamond, black coal, or it could be diamond. Okay. Oh, there is one of those planetary nebulae. Here's that white dwarf in the middle, and it's blown off when that went from helium, hydrogen, the instability, to blow off the outer layers of the gases and leave just the core here as a white dwarf. over time that will cool and you won't see it anymore because it's not producing any light. That was your white dwarf surrounded by your planetary nebula. So a slightly different picture from the one we saw earlier. Okay. Now, let's go to the most massive stars. Well, the massive stars, not the most massive, but massive. More mass, more gravitational contraction, more heating. Now your critical temperature goes up to 600 million K. Way high. Now you have enough for the carbon to fuse. And when the carbon fuses, you get the heavier nuclei, one after another, up to, but no further than iron. Now later, in the next chapter or two, we'll find out that iron is the very most prevalent element in our Earth. The core of the Earth is almost totally iron, with a fair amount of nickel and magnesium, but iron is predominant. And that's why. Because the ultimate fate of most of your fusion is iron. Okay? This is in the big stars anyway, when you get up to 6 million K temperature in that gravitational collapse. Now, after you reach iron, all the fusion energy sources are used up. Because beyond iron, it goes in a different direction. So iron is about what you get. The energy expansion pressure is lost. So the dynamical equilibrium is disrupted. It collapses on itself. And now you get what they call a supernova. The star collapses, but it collapses rather, and this is on geologic time, rather quickly, but it collapses on itself and then rebounds. It's just like the basketball hitting the wall and bouncing back at you. It collapses and then rebounds from the core. The elements beyond iron, because that rebound now fuses things together more than you get from this fusion, and the elements beyond iron are created in that explosion, which is a massive explosion, and those are distributed throughout the universe. So that's why we have things on the periodic table beyond iron. Iron is just right down here at number 26. That's about a fourth of the way through the periodic table. Naturally occurring through fusion, iron is the maximum, but when you have that massive explosion, when it rebounds from the core, that explosion that happens there, that creates the heavier nuclei here. It's not, I guess it is a type of fusion, but it's not the same type that we had before. So that's where you get these others. But yeah, guess what? Anything beyond iron and sort of nickel and copper and zinc, some of those near iron, after that, these get rarer and rarer and rarer. There's silver down here is rare, gold is rare, platinum is rare, everything else down there is pretty rare because iron is the most prevalent. Okay. What happens beyond here? Again, it depends on the mass of the remaining core. Everything depends on that mass of the remaining core. So you've had a couple of contractions. You started with hydrogen to helium fusion, then you got helium to carbon fusion, then you got carbon to iron fusion, or a series of things up to iron, and then you had this massive explosion, the supernova, blowing things out, which made the heavier nuclei. And now, what happens from there? What is remaining in the core? Well, how big is your core? Okay? And I think we're going to have to stop there. Sorry about that. We've run out of time. I know y'all wanted to go on, didn't you? Are y'all exhausted yet? I'm pretty close. Okay. All right. I think where we're going to be, I know y'all don't have your books, but I'm trying to mark it in the book, so I'll start on the right slide. It's just past supernova. Okay, so it's just about here. And this is going to be, I can't see a slide number, but y'all remember it's end states for massive stars. All right, y'all have been a great group. I hope we'll get enough others to come in. I would hate for this whole day of lecture to be wasted, but it was fun anyway.